How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And our business today is the idea of center of gravity. A marvelous thing to consider, really, and fantastic in its consequences for the human race. Consider the following. I have here a double track which is downhill to my left. Here I have a cylinder of wood which, as you know, will go downhill, as any respectable cylinder should do. But here I have another geometrical form, and I put it at the bottom of the plane, and lo and behold, it goes uphill. And that's a strange business. Well, friction forces are holding it there, so you see, it goes uphill. And a proper understanding of this lies in an understanding of center of gravity, an idea we got first from Archimedes in about the 3rd century BC. Consider a stick, a meter stick. If it was a good stick, as I would like to have it, it would have to be uniform, homogeneous, and isotropic. Those are wonderful words to know the meanings of. Supposing the stick weighs 10 pounds, and I support it with 2 fingers like that. It is clear that each finger pushes up with 5 pounds each. 5 plus 5 is 10, the stick weighs 10 down. Indeed, if I move the fingers elsewhere, I still exert 10 pounds up, but in 2 places. Now, can I not find a place such as that right there, where I exert a force of 10 pounds up? And we are then led to say that all the stick is right there, all of it, and that's the center of gravity of the stick. Incidentally, I could use also the phrase center of mass, and I leave it as an exercise for you and your teachers to find the difference in center of mass and center of gravity. Now, I said all the stick is here. This suggests that there's no stick here and no stick here. And somebody says, but I see some stick here. And I say, all the stick is right there. And I could prove it. Let me put a clamp on the stick and support it somewhere remote from the center of gravity. If I do that, the stick tips. Obviously, anybody knows that. But if now I put another clamp on the other side and find an appropriate weight here, you will see an astonishing thing, that I can put the stick in equilibrium on the ground that all the weight is at the 50 mark. So, on the blackboard, it would look like this. Here is the stick. There is the center of gravity in the geometric center, and I have supported it right here with a weight hanging here. And I say that if we consider all the weight of the stick, W sub S, acting right there, then that weight of the stick times that distance there is equal to this weight times this distance here. And so we can find the weight of the stick without weighing it by assuming all the stick is right there. Now, to prove that you are right when your teacher does this, all you need to do, having done the mathematics, is to put the stick on a platform balance in such a fashion and weigh it. And an astonishing thing is discovered. A very astonishing thing. That the weight of the stick is exactly what you get, disregarding some little experimental error, exactly what you get by assuming all the stick there. Let's consider it further. Here is an equilateral triangle. If I put a pin through one vertex or corner and hang a plumb line on there, a plumb line is just a string with a bob on the end of it, and such a plumb line is always vertical for the observer at the place in question, and then I draw a line on that triangle, I say that the center of gravity lies somewhere on that line. Proof. Let me do this from another corner, such as, say, this one, which isn't broken. And we see that the plumb lines intersect at a place. This place is the center of gravity of this triangle. All the triangle is right there. Proof. I am going to put my finger right there and the triangle will remain in a horizontal plane, which was announced by Archimedes, again in the 3rd century BC, in a classical book which he wrote entitled De Equiponderantibus, see, concerning equal ponderousness. You can discuss this with your classmates and your teacher. So the center of gravity of this equilateral triangle, for those of you who know a little geometry, is at the intersection of the medians, at the intersection of the angle bisectors, at the intersection of the altitudes upon the sides, reviewing a little bit of Euclidean geometry. Consider another triangle, an isosceles triangle, the center of gravity found in the same way. Or consider an irregular body, center of gravity found in the same way, the intersection of the plumb lines. Of course, the center of gravity of a uniform circular plate would obviously be in the very center. Now, in all of these illustrations, we have found the center of gravity to be where? Where there is some stuff. There's some stuff there. So the question has very intriguing complexion, because here, if I hang this up and drop a plumb line, it goes so. If I now drop another plumb line, it goes so, and we see a most remarkable thing, very remarkable. The plumb lines intersect where there is no stuff, right in here. And this is the center of gravity of this slab. Moreover, all the slab, all the plate, may be considered to be right here where there is none, which is a most astonishing piece of business. So the center of gravity of a system can be where there is no stuff of the system. This leads me to ask, where is the center of gravity of a donut? The center of gravity of a donut is in the middle of the hole. And if you cut out the middle of the hole, or cut out the hole, I have in my right hand the center of gravity of this donut, which is a very remarkable idea. Now, to show you the consequences of this, let's look at this rolling down business. The uniform cylinder rolls downhill. Its center of gravity is in the geometric center, along the long axis and in the middle. If we measure the height of the center of gravity above the tabletop, which I would call the zero potential plane, measure it there, then measure it down here, we would find that this is lower than this. Accordingly, the center of gravity has gone downhill, which introduces another very fundamental principle, namely that the energy of a system tends toward less. So this goes downhill. The center of gravity has gravitated downhill. On this one, the center of gravity of this double cone, referred to as a cone of two nappes, N-A-P-P-E-S, beautiful geometry established by René Descartes, the Frenchman. The center of gravity of this double cone lies along this central axis and in the middle of this single base. So when I put the cone here, the center of gravity is so high above the zero potential plane, the tabletop, and where is it now? It is clearly nearer the tabletop. So again, the center of gravity has gone downhill, although it looks as if this is a crazy piece of business, that the cone, stuck a little by friction there, the cone appears to roll uphill. So the center of gravity, very important idea. More of an astonishing nature. Here is a cork stopper. Here is a cork stopper with a pin in it, and there's the head of the pin. Here is another cork stopper with a pin in it, and that's the point of the pin. And if I put these point to head in this position, if I can find that position here, and let go, obviously it will not stay stably. It will tip over. Why? Because the center of gravity is above the point of support, a condition that is not good for equilibrium. So what do? I put a couple forks in here, in any way whatsoever, and then I put the point of the pin on the head of the pin, And there it is. Let me get this away so it doesn't hit the glass vessel. And we see an astonishing thing. Just look at that. Should not that fall off? It should. But why doesn't it? It does not fall off for this reason. The center of gravity of this system is below the point of support, which is another condition of equilibrium. Here's a good illustration of it. Take this little man, a little metal figure in the shape of a man who supports himself, you see, on the toe of one foot. And that's fantastic, really. He is very stable. If I tried to knock him off, oh, that just slipped there. That didn't really fall off because of the inadequacy of the center of gravity. Look at that. What must we say? We must say this, that the center of gravity of this man and his rod and the sphere system is below the point of support, which makes him stable. I say the idea of center of gravity is an astonishing one, as I remarked earlier, in its consequences for the human race. Consider this one, more of the same. And I hope you see that I am injecting into this program some elements of fun and jest, because, as I like to say, the intellectual process is usually very severe, so it needs some fun injected into it to make it a little more palatable. Here is a figure most stable for the same reason, the center of gravity below the point of support. Of now fundamental interest to us is such a program as I have here. Consider this block of wood. Square cross-section, cut askew on the bottom. It is so stable. I call your attention to a plumb line that is supposed to be inside at the center of gravity, and that plumb line falls inside the base. Now, let me put another block atop the original. I hope you see what has happened. I have raised the center of gravity and shifted the plumb line to your left, my right, so that the plumb line passes more nearly on the inner edge of the base. The system is now less stable. If now I put another block atop, it is obvious what the consequences are likely to be. The center of gravity has been raised, the plumb line is shifted further to my right, and may indeed fall outside the base. This makes the system unstable, as you will now see. Notice, the slightest displacement is likely to tip it over. So, if a system is stable, as we say in physics, what we mean is this. Any slight displacement from its position of equilibrium will still allow it to return to where it was. If it is unstable, as we have now, because the plumb line falls outside the base, any slight displacement will raise havoc with us. Watch it. And it tips over. You know what I am representing here. I am representing the Tower of Pisa, which I hope you know about historically, and I thought you would like to see a picture of it. In Pisa, in Italy, and I hope one day you will go there to see it for yourself. I say it is a most wonderful thing to contemplate. So, ladies and gentlemen, and boys and girls, we come to the end of our first lesson, let us say, on the great idea of center of gravity, the notion first established by Archimedes. And I thank you for listening. How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And our business today is the idea of center of gravity. A marvelous thing to consider, really, and fantastic in its consequences for the human race. Consider the following. I have here a double track which is downhill to my left. Here I have a cylinder of wood which, as you know, will go downhill, as any respectable cylinder should do. But here I have another geometrical form, and I put it at the bottom of the plane, and lo and behold, it goes uphill. And that's a strange business. Well, friction forces are holding it there, so you see, it goes uphill. And a proper understanding of this lies in an understanding of center of gravity, an idea we got first from Archimedes in about the 3rd century BC. Consider a stick, a meter stick. If it was a good stick, as I would like to have it, it would have to be uniform, homogeneous, and isotropic. Those are wonderful words to know the meanings of. Supposing the stick weighs 10 pounds, and I support it with 2 fingers like that. It is clear that each finger pushes up with 5 pounds each. 5 plus 5 is 10, the stick weighs 10 down. Indeed, if I move the fingers elsewhere, I still exert 10 pounds up, but in 2 places. Now, can I not find a place such as that right there, where I exert a force of 10 pounds up? And we are then led to say that all the stick is right there, all of it, and that's the center of gravity of the stick. Incidentally, I could use also the phrase center of mass, and I leave it as an exercise for you and your teachers to find the difference in center of mass and center of gravity. Now, I said all the stick is here. This suggests that there's no stick here and no stick here. And somebody says, but I see some stick here. And I say, all the stick is right there. And I could prove it. Let me put a clamp on the stick and support it somewhere remote from the center of gravity. If I do that, the stick tips. Obviously, anybody knows that. But if now I put another clamp on the other side and find an appropriate weight here, you will see an astonishing thing, that I can put the stick in equilibrium on the ground that all the weight is at the 50 mark. So, on the blackboard, it would look like this. Here is the stick. There is the center of gravity in the geometric center, and I have supported it right here with a weight hanging here. And I say that if we consider all the weight of the stick, W sub S, acting right there, then that weight of the stick times that distance there is equal to this weight times this distance here. And so we can find the weight of the stick without weighing it by assuming all the stick is right there. Now, to prove that you are right when your teacher does this, all you need to do, having done the mathematics, is to put the stick on a platform balance in such a fashion and weigh it. And an astonishing thing is discovered. A very astonishing thing. That the weight of the stick is exactly what you get, disregarding some little experimental error, exactly what you get by assuming all the stick there. Let's consider it further. Here is an equilateral triangle. If I put a pin through one vertex or corner and hang a plumb line on there, a plumb line is just a string with a bob on the end of it, and such a plumb line is always vertical for the observer at the place in question, and then I draw a line on that triangle, I say that the center of gravity lies somewhere on that line. Proof. Let me do this from another corner, such as, say, this one, which isn't broken, and we see that the plumb lines intersect at a place. This place is the center of gravity of this triangle. All the triangle is right there. Proof. I am going to put my finger right there and the triangle will remain in a horizontal plane, which was announced by Archimedes, again in the 3rd century BC, in a classical book which he wrote entitled De Aqui Ponderantibus, see, concerning equal ponderousness. You can discuss this with your classmates and your teacher. So the center of gravity of this equilateral triangle, for those of you who know a little geometry, is at the intersection of the medians, at the intersection of the angle bisectors, at the intersection of the altitudes upon the sides, reviewing a little bit of Euclidean geometry. Consider another triangle, an isosceles triangle, the center of gravity found in the same way. Or consider an irregular body, center of gravity found in the same way, the intersection of the plumb lines. Of course, the center of gravity of a uniform circular plate would obviously be in the very center. Now, in all of these illustrations, we have found the center of gravity to be where? Where there is some stuff. There's some stuff there. So the question has very intriguing complexion, because here, if I hang this up and drop a plumb line, it goes so. If I now drop another plumb line, it goes so, and we see a most remarkable thing, very remarkable. The plumb lines intersect where there is no stuff, right in here. And this is the center of gravity of this slab. Moreover, all the slab, all the plate, may be considered to be right here where there is none, which is a most astonishing piece of business. So the center of gravity of a system can be where there is no stuff of the system. This leads me to ask, where is the center of gravity of a donut? The center of gravity of a donut is in the middle of the hole. And if you cut out the middle of the hole, or cut out the hole, I have in my right hand the center of gravity of this donut, which is a very remarkable idea. Now, to show you the consequences of this, let's look at this rolling down business. The uniform cylinder rolls downhill. Its center of gravity is in the geometric center, along the long axis and in the middle. If we measure the height of the center of gravity above the tabletop, which I would call the zero potential plane, measure it there, then measure it down here, we would find that this is lower than this. Accordingly, the center of gravity has gone downhill, which introduces another very fundamental principle, namely that the energy of a system tends toward less. So this goes downhill. The center of gravity has gravitated downhill. On this one, the center of gravity of this double cone, referred to as a cone of two nappes, N-A-P-P-E-S, beautiful geometry established by René Descartes, the Frenchman. The center of gravity of this double cone lies along this central axis and in the middle of this single base. So when I put the cone here, the center of gravity is so high above the zero potential plane, the tabletop, and where is it now? It is clearly nearer the tabletop. So again, the center of gravity has gone downhill, although it looks as if this is a crazy piece of business, that the cone, stuck a little by friction there, the cone appears to roll uphill. So the center of gravity, very important idea. More of an astonishing nature. Here is a cork stopper. Here is a cork stopper with a pin in it, and there's the head of the pin. Here is another cork stopper with a pin in it, and that's the point of the pin. And if I put these point to head in this position, if I can find that position here, and let go, obviously it will not stay stably. It will tip over. Why? Because the center of gravity is above the point of support, a condition that is not good for equilibrium. So what do? I put a couple forks in here, in any way whatsoever, and then I put the point of the pin on the head of the pin, And there it is. Let me get this away so it doesn't hit the glass vessel. And we see an astonishing thing. Just look at that. Should not that fall off? It should. But why doesn't it? It does not fall off for this reason. The center of gravity of this system is below the point of support, which is another condition of equilibrium. Here's a good illustration of it. Take this little man, a little metal figure in the shape of a man who supports himself, you see, on the toe of one foot. And that's fantastic, really. He is very stable. If I tried to knock him off, oh, that just slipped there. That didn't really fall off because of the inadequacy of the center of gravity. Look at that. What must we say? We must say this, that the center of gravity of this man and his rod and the sphere system is below the point of support, which makes him stable. I say the idea of center of gravity is an astonishing one, as I remarked earlier, in its consequences for the human race. Consider this one, more of the same. And I hope you see that I am injecting into this program some elements of fun and jest, because, as I like to say, the intellectual process is usually very severe, so it needs some fun injected into it to make it a little more palatable. Here is a figure most stable for the same reason, the center of gravity below the point of support. Of now fundamental interest to us is such a program as I have here. Consider this block of wood. Square cross-section, cut askew on the bottom. It is so stable. I call your attention to a plumb line that is supposed to be inside at the center of gravity, and that plumb line falls inside the base. Now, let me put another block atop the original. I hope you see what has happened. I have raised the center of gravity and shifted the plumb line to your left, my right, so that the plumb line passes more nearly on the inner edge of the base. The system is now less stable. If now I put another block atop, it is obvious what the consequences are likely to be. The center of gravity has been raised, the plumb line is shifted further to my right, and may indeed fall outside the base. This makes the system unstable, as you will now see. Notice, the slightest displacement is likely to tip it over. So, if a system is stable, as we say in physics, what we mean is this. Any slight displacement from its position of equilibrium will still allow it to return to where it was. If it is unstable, as we have now, because the plumb line falls outside the base, any slight displacement will raise havoc with us. Watch it. And it tips over. You know what I am representing here. I am representing the Tower of Pisa, which I hope you know about historically, and I thought you would like to see a picture of it. In Pisa, in Italy, and I hope one day you will go there to see it for yourself. I say it is a most wonderful thing to contemplate. So, ladies and gentlemen, and boys and girls, we come to the end of our first lesson, let us say, on the great idea of center of gravity, the notion first established by Archimedes. And I thank you for listening. How do you do, ladies and gentlemen? I am Julius Sumner Miller, and physics is my business. And I should say, how do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today is the subject of inertia. And I must make the matter, the idea clear, as follows. Here we have a block of wood at rest on the tabletop. And I ask, what does that block want to do? Answer, the block wishes to remain at rest. Supposing now I have double as much block, and I try in turn to put that system in motion. What do I discover? It also wishes to remain at rest. Moreover, it wishes to remain at rest twice as much, and therefore we say its inertia is twice as great. And so you discover at once that I have used the term inertia and referred to the idea of mass as synonymous. So mass and inertia are synonymous. And this is all tied up beautifully in Newton's first law, which says what? If a body is at rest, it wishes to remain at rest. And if it is moving uniformly in a straight line, that's what it wants to do. In English, simply, whatever a body is doing, that's what it wants to do. Let's look at Newton's Latin for it. Newton put it in Latin. Axiomata sive legis motus. Axioms, even laws of motion. Corpus omne perseverare in statu suo quiescendi, and so on. And in English, a little more within our competence. Every body continues in its state of rest or of uniform motion in a straight line, unless there are some forces to divert it. Consider now the following. Here you come on April Fool's Day, let us say, on a package, on two packages resting on the ground. Here is one and here is another. And you deliver, you impose a force on the one. I will, instead of with my foot, with my hand, and it experienced such a motion. The force produced a motion in the body of so much inertia. Now I try it with this one. Hardly as much motion. Why? This one is filled with rags, and this one with two bricks, and this one has the greater inertia. So, the measure of the mass of a body is its inertia. Consider now the two aspects of Newton's first law. A body at rest wishes to remain so. Here I have a heavy block of wood, a hole in it, and I put a dowel rod in the hole. The dowel rod constitutes the handle. How can I put that handle into the block? As follows. As follows. Notice what happens. I hit the handle. The block remains at rest, whereupon the handle moves into the block. That's the first law. The body of large inertia wishes to remain at rest. Let me pursue this in another way to demonstrate the second part of Newton's law. What did the second part say? If the body is in uniform motion in a straight line, that's what it wants to do. I start again. Now I come down on a firm block. The motion of the handle is arrested. The handle and the block were moving. And what does the block want to do? Keep moving. Whereupon it lodges itself more firmly on the handle. Thus do we demonstrate Newton's first law in two parts. Let me do this another way. Very pretty. Very pretty. I have a support and a weight W supported by a string and another string with a loop in it here, which I shall show you. Let me call this string A and this string B. I propose to do as follows. I'm going to pull on string B, the lower string. And I can break either string B or string A by invoking Newton's first law. If I pull suddenly on string B, W wishes to remain at rest, and B will break. On the other hand, if I pull gently on B, A supports W, already there, plus the force I impose. And I shall show you that exactly with this demonstration. Here is a string. Here is a hook. Here is a weight. and the upper string is supporting the load. Here is the lower string, and I am putting a little rod inside here so that my hand is not underneath should the weight fall. I am going to break the lower string. Watch it now, the lower one. There it is, I broke it. Now I am going to change the string. I'm going to change the string. And now I am going to break the upper string by pulling slowly on the lower one. Watch it now. Watch. We hope that breaks. Now, supposing it does not. One is led to say the experiment has failed. And I say, no, the experiment doesn't fail. I have failed to meet the requirements of nature. Watch. I'm going to break the upper string. There it is. And so we can be applauded for success. Consider another demonstration of the same. Here is an enormous weight, 16 pounds. Here is a string attached to it. If I pull on that string in a gentle way, I'll do it by hand, in a gentle way, the string can support the load. Now let me try to accelerate it. What does Newton's first law say? Body wants to remain at rest. It has enormous inertia. Watch it. Do you see? The string has broken. I shall have more to say about this when I talk about Newton's second law. The second law. Consider now another dramatic demonstration. An application of Newton's first law, because we must not escape the fact that these laws of physics, of nature, of science, have vast applications in plebeian things. A brick, a trowel. Cannot the craftsman, the bricklayer, utilize Newton's first law in this way? Notice if he hit his hand with the trowel, he'd hurt it. But he can hit the brick with absolute abandon and feel nothing. Inertia of the brick. Here is another classic, which I like to do because it is so dramatic. A sheet of paper, about 20 inches by 30. 20 inches by 30. 600 square inches. The load on each square inch is roughly 15 pounds. Atmospheric pressure at sea level. Therefore, about 9,000 pounds of air on that paper. That's enormous inertia. Proof. Here is a board, 1/4 inch thick. I put the board under here, and now I am going to try to put that enormous mass of air into motion by a sudden impulsive blow on this end of the stick. The impulsive view that people have is, oh, the whole thing will catapult. No, it will not, because that mass of air is at rest, and Newton said it wishes to remain so. Watch it. It did not move. It did not move. Fantastic. Now, remember, ladies and gentlemen and boys and girls, when I refer to this block being at rest, and then I say, what does it want to do? And the answer is it wants to remain at rest. I would not have you dispose of this as trivia, because it took the genius of an Isaac Newton to establish it. Nothing trivial about it. Consider another dramatic demonstration. Oh, this one is a beaut. Here is a vessel of water, and it has quite some inertia, and I put it on this paper, and I move it slowly, slowly. Remember, this has large inertia. It wants to remain at rest, and I am not trying to accelerate it too rapidly, and thereby friction forces hold it onto the paper. And so I pull more and more and more and more. We're in a little trouble because friction isn't right for me. But anyone in his right mind must testify to the prospect, if I continue in the manner I have been doing, the whole thing will fall down. But if I invoke the laws of Newton, the first law, which says it wants to remain at rest and will refuse to be moved by short-lived impulsive forces, watch it. Are you not surprised that it stayed there? Consider another, more application. Here is a vehicle, and here is a body standing upright in the vehicle. And now I want to show you that if I move the vehicle, The body is at rest with respect to it, and what does it want to do? It wants to stay there. Watch it. And so it did. And that's why when you accelerate a car rapidly from a standstill, your head is jerked back because of the large inertia of the head. On the other hand, if the car is moving uniformly, if I now suddenly arrest its motion, what will the block do? Well, the block was going straight, and that's what it wants to do. Oh, notice I accelerated too fast the first way. There it is, and the block tipped forward. A quick one for your inquiry. Here I have two vessels, and remember the subject is inertia. They each contain 1 pint. And let us say that one is filled with cream and the other with milk. So I have a pint of milk and a pint of cream. Quickly, which has the greater inertia? That's equivalent to asking which has the greater mass. That's equivalent to asking which has the greater weight. And some are led to say, oh, the cream, of course, because it's thick and sluggish and viscous. Oh, no, mistake. The milk has the greater inertia for reasons, of course, you see clearly yourself. The pint of milk weighs more than the pint of cream. Another demonstration of the inertia again. Here is a stack of coins. They happen to be Australian pennies. Why? Because they have larger inertia than US pennies. And now what can I do? With a thin blade, I can deliver a sharp, impulsive blow to the lowermost one, and what do I hope to see? I hope to see the whole stack remain unmoved. Why? Because it's at rest and wants to stay. There it is. There it is. There it is. And I just love that demonstration. Why? Because it is a classic revealing the beauty and strength and simplicity, in a sense, of Newton's first law. I want to show one more. Remember what the second part of the law said. I would urge you never to forget that the first law has 2 parts, which are rarely ever properly separated. I said a body moving in a straight line wishes to continue so. Here is a ball swinging in a vertical plane, in a vertical circle. I would remind you that at the instant in question, when the ball is right there on the end of the string, its motion is tangent to the path at that place, and if I should cut the string or let go of it, the ball would not go radially outward, but would go instantaneously in a direction tangent. So this introduces here in a passing way the idea of centrifugal force, which is a nasty thing to handle, and often much is said that is wrong. But if I let go of the string at the top, where will the ball go? Tangent. Watch it. There it is, tangent. Now, it is proper, before we conclude a program on Isaac Newton, to show you one of many photographs of Newton. A very important place this man occupies in the history of humankind. And I would hope that when you go to London sometime, you will most certainly go to Westminster Abbey and see where he is buried. And what does it say on that beautiful epitaph? Among other things, let men rejoice that so great a one has existed. So we are coming shortly to the end of the program. One final enchanting thing, an array of cups. If I put this heavy block on them gently, I can drive this spike into that block without the cups feeling anything. Why? Why? Because the block has enormous inertia. If, on the other hand, I drop it, it's going and it wants to keep going. There it is. And thus I conclude, ladies and gentlemen, a program on inertia. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our special business today is Newton's second law, the second law. Now, in an earlier program, we discussed the first law, and I showed you some dramatic demonstrations on the first part, a body at rest, and on the second part, a body moving uniformly wants to do that. Now we come to Newton's second law. This is a staggering thing in its implications and very, very difficult, really. But what students of physics learn somewhere in their course is that Newton's second law says F equals ma. And indeed, that's what it says. But that's powerful and not so easy. Let us see what Newton said for his second law. In the Latin, mutationem motus proportionalem esse vi motrici, but the Latin is a little old-fashioned, so if we look at the English, here it is. Change of motion is proportional to force applied and takes place in the direction of the straight line in which the force acts. So, let me demonstrate Newton's second law. Here I have two carts, a heavy one, a massive one, and a less massive one, and they are connected with a pseudo-spring, an array of rubber bands, which are called elastic bands, but which incidentally are inelastic. Now they are on wheels so that they move rather freely, but we learned earlier that this one has less inertia than this one. Now, when I pull them apart and stretch the spring between them, the same force acts on both. And let us see if we cannot at once predict what will happen. If we apply Newton's second law to the forces acting on these cars, clearly the big car will have a little acceleration and the little car will have a big acceleration. That's an obvious thing to speculate on. Watch it. I'm going to pull them apart. There is one and the same force acting on both cars, and you will observe that the smaller one gets going the faster sooner, of course. And so, here is an expression mathematically that describes this. And what do we learn from that remark? We learn that the accelerations are inversely proportional to the masses. The bigger the mass, the less the acceleration. Now, this experiment with the two cars, very important for our concern later, because we will talk in subsequent programs about the energy possessed by each car and about the momentum possessed by each car, and we shall learn then that Newton's second law has enormous implications for later work in physics. Now, more about the second law. Here is a scale on which I hang a weight. And I don't care what the scale reads. It reads something. We say it reads the weight of the body. But I really don't know what that means. Nor did Newton, because, as we believe, gravitational forces, the Earth pulls on this, stretches the scale. But remember, even Newton said, I offer no hypothesis concerning gravitation. Now, do we understand it today? But anyway, this scale reads the weight of this. So I'm going to write Newton's second law saying that very fact. Here it is. F equals mg, where mg is the weight of the body. Now I'm going to accelerate this system upward. And I want you to see what the scale does. Watch it now. The scale read more. And so I have to add here ma. In other words, the scale reads not only the rest mass of the body, but an additional force which was required to accelerate it upward. Let me now start again in the zero position, the system at rest, the scale reading the so-called weight of the body, and let me accelerate downward. Watch it. The scale reads less, and so I write minus ma, mg minus ma. And this tells us a wonderful thing, because if I were to go to the edge of my roof and hold this like this, and then let go of it here, and the whole thing fell down toward the earth, a good question to ask is, what would the scale read during the falling? And the answer is obvious. Since the acceleration downward would be that of a freely falling body, the scale would read 0. So if I should jump off from my tabletop while I am in flight toward the earth, I am weightless. I am weightless. Now, this second law bears on the first one, which I showed in an earlier program. You remember that I had an enormous weight here, on which I pulled gently with a string, and the string held it. But when I gave the system a sudden acceleration upward, the string cannot endure it. And I said then that the body wishes to remain at rest. I now add an additional fact, that the string must exert a force not only equal to the weight of the body, but an additional one to accelerate it, which it may not be able to do. No, it couldn't do it. Now, what is the meaning of this for other things? Supposing I had an enormous sphere, such as I have here, a steel sphere, 2 inches in diameter, and then a teeny-weensy one, and I want to show you that. I want to show you that. In fact, here I have several of different sizes. There's one, there's one. Very good. Now, I have one in here that is so tiny, in fact, that I can't see it without my glasses. That shows you how tiny it is. And I wonder, if I get the other debris out of the way, can the camera get that little one? Right. Well, it's there. I assert it is there, even though you cannot see it. Oh, yeah, it's awful tiny. And what am I going to say about it? Supposing I hold these two, I won't hold the tiny one because you can't see it. Supposing I hold these two at the same horizontal level, above the level of the earth equally, and I let them go. They fall with the same acceleration. Proof. Newton's second law. Proof. F equals ma is the generic expression for Newton's second law. Now, what is the F acting on this body? The F acting on that body is its weight. And when I let it go, what is its acceleration? It has a certain mass m. Its acceleration is g. So these two equations, you see, this, the generic one, F equals ma all over the universe, so we think, and W equals mg for earth-dwelling creatures who wish to look at the weight of a body. So you can see that if I double the mass of any body, I would at once double its weight, and its acceleration remains unaltered, which is a sort of explanation why all bodies have the same free fall acceleration, as Galileo showed in the 17th century. Now, this is quite remarkable, because one is led to think, why? I can't believe that this one will not fall faster than this one, and this subject is taken up very excellently by Galileo in his dialogues concerning two new sciences, where I urge you to read the discussion between Sagredo and Salviati and Simplicio. Now, there are some further implications of the second law which have some levity. I like physics in cartoons, and here is a cartoon that I recently saw. Here is a little boy, and there is a bathroom scale, and here is another little boy, and they weigh, by all looks of things, about 70 pounds. Now, it's obvious what has happened. This one jumps down onto the scale. And what is the caption under the picture? Wow, he says, wow, 140. You can see that this is Newton's second law. F equals mg plus ma because of the force delivered through his acceleration to the scale. And I think that's terrific. Let's consider another such problem. Here is a smooth pulley fixed, say, to a solid beam up there. And here is a rope over the pulley. And here one man stands holding the rope. And here an identical weighted man stands holding this rope. And they are both on the ground. Question. The man A climbs the rope. B just holds on. He just stays there. Question. What happens to B? Answer. B gets a free ride. For whatever A does is felt by the rope and in turn by the man. And so this is really Newton's second law. Two men on a pulley. Now, a more dramatic event, much more dramatic. Here is a scale which reads from 0 to 2,000 grams, and I put 1,000 on it, and clearly the scale reads 1,000. If I put 2,000 on it, at rest, remember, at rest, the scale reads 2,000. Now what am I going to do? I am going to put the scale on a horizontal plane on that board in such a fashion with a pulley here and a rope and a pulley here and a rope, and I'm going to put 1,000 there and 1,000 right there, so that I have 1,000 pulling to the right and 1,000 pulling to the left. I'm going to do that right now. There's 1,000 on the right, and I've got to hold that. Now I get over here and I put 1,000 on the left, and then I cover it over, as I like to say for my students, so that evil eyes do not see it. And remember now, we ask the classic question. When I had 1,000 on the scale in the vertical line, it read 1,000. When I put 2,000 on it in the vertical line, it read 2,000. We want to know, what does the scale now read? 1,000 pulling to the right, 1,000 pulling to the left. Several answers. One, oh, says somebody, it reads 0, since the forces annul each other. No, no, says somebody else. 1,000 to the right, 1,000 to the left, it reads 2,000. And I must tell you that whatsoever your point of view, these are both wrong. So I could leave it as an exercise for you to do, but since I have a kind heart, I will tell you that the scale reads 1,000 grams. But having told you this, I urge you very seriously to explore why that is so. One further little comment. Oh, I want you to see another picture of Newton. I showed an earlier photograph in his later years, and here is one as a young man, 17 years old, when he entered Trinity College in Cambridge, a genius the like of which the human race has not yet again seen. One last experiment. Newton's second law. Here I am going into an elevator on the ground floor. The push of the floor of the elevator when at rest is my weight plus the weight of the bag. Now the elevator accelerates upward. You know what happens. Your knees buckle and the load is pulled out of your hand. No, 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 not pulled. It wanted to stay at rest. It was at rest, and that's what it tried to do. But what is the explanation of the added tension in my arm and the bending of my knees? Answer, F equals mg plus ma. Now the elevator is on an uppermost floor and starts down. You know what happens? Your belly feels empty. F equals mg minus ma. And so we have a better understanding of the laws that envelop us by applying the laws of Newton. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the very special third law in Newton's three laws of motion. And to view it at least once in our lifetime in the Latin, I have it here. Lex 3. Actione contrariam semper et equalam esse reactionem. Now, if you didn't know any Latin at all, you'd see something in there about action and reaction. And indeed, that's what it sums up to be. Third law, to every action, there is always an equal and opposite or contrary reaction, or the mutual actions of any two bodies are always equal and oppositely directed. Now, a strange introduction to this law would be as follows. Consider me standing still and quiet on the earth, and I jump up in this manner. I ask, did you feel the earth recoil? And the answer is, it must be, it did indeed recoil, even though you may not have felt it. Why? Here is the earth, enormous mass. Here I am, a teeny-weensy creature of little mass. I push down on the floor with a force F, which acts on me and on the earth. And as before in the second law, my little mass, you detect, has an enormous acceleration. Up I go. But the earth, having an enormous mass, has a teeny-weensy acceleration, which you cannot detect. So, consider Newton's third law in a toy. Here is a little vehicle with some wheels, to which is fixed a rubber balloon, and I blow some air in the balloon. Now I'm going to let the air come out of a certain hole, orifice here. The air comes out this way, and what must the vehicle do? The vehicle must go the other way. Watch it. There it goes. And so I am reminded of a certain exercise that goes like this. Here is a rocket vehicle. We have some stuff in here in a state of combustion. The products of the combustion come out here, millions of little particles of stuff. Now, many people have the distorted notion that this stuff coming out here must push against the atmosphere in order for this to go. And I say that is utterly erroneous. This system, this vehicle, works better where there is nothing, because we want the little mass of stuff coming out there to come out with the greatest possible velocity and hence have the greatest rate of change of momentum, the product of m and v being momentum. Now, I'm going to go back to the two cars, because the case of the two cars, I said earlier, very important. Massive car, less massive car. I stretch the spring between them. One and the same force acts on both, and we witness an astonishing thing. Here is the massive car, here is the little car, less inertia, there is the spring. Now, what did we see? The same force acted on both. But you notice that the smaller one had the bigger acceleration, and the bigger one had the lesser acceleration, and therefore, in the same time of travel, and they would both travel the same time from time zero to the time of collision, clearly the smaller one has the higher velocity. So, writing the momentum of both cars, we would equate it as follows. The large car has a little velocity, the little car an enormous velocity, and these momenta are equal. Very important that you see that point, that the same force acts on both, the accelerations are inversely as the masses, and the momenta are equal. In another program, I will talk about their energies, and we will discover a very strange thing. Now, more on this conservation of momentum, which is essentially Newton's third law. Here I have a CO2 cartridge, gas in here under enormous pressure. Here is a carriage in which I put it. I'll look around that end. And you will notice that there is a barrier on this end of the cartridge, of the carriage. Now what am I going to do? I am going to make a hole in this end of the cartridge. The gases come out this way. Oh, I erased that before. The gases come out this way, and they have a certain momentum, their mass and their velocity. The vehicle must go the other way. Watch it now. Watch. There it goes. There it goes. Millar's earthbound rocket. Now, a very important thing. It fled away. Fled away. Momentum, I'm sure. I would have asked a question had I had it in hand. Question. I would feel it to be very cold. Very cold. And I want to know, why is it cold? A second question. There could indeed be frost on it. And the question is, where cometh the frost? In the first question, we have a very powerful piece of physics. The gases coming out must do work. This costs energy. And I leave it there for further discussion in another program. Now, let's go to something still more dramatic. Again, conservation of linear momentum. Here is an array of steel spheres, highly elastic. Steel is highly elastic. By that I mean, when they are deformed, they recover. They lie in the lowest potential configuration. I take one up the plane, let it go, having given it some potential energy, and it collides with the system at rest, and watch what happens on the remote end. 1. Oh, that's terrific. Watch it. Look it. Nearly instantaneously. Indeed, I'm led to ask, how fast does the impulse get down there? Answer, with the same velocity as the velocity of sound in steel, which is about 15,000 feet per second. So if this were a foot long, oh, that's more likely a foot long, that's 9, 12 inches. Watch it. One 15,000th of a second. You notice, too, that the whole system experiences some motion. That's because they all wish to seek a lower potential plane. Now, 1 at collision mv. 1 goes away mv. Watch 2. 2 mv plus mv, 2 mv. Now let us disregard the intermediate or the other motions that we witness, because a discussion of this would divert me from my purpose here. All I wish to say is that whatever the momentum before the collision, so that is the momentum after. 1, 1. 2, 2. 3, oh, notice they are seeking a lower potential plane. The energy of a system runs downhill. 3, oh, that's pretty. Notice they are seeking a lower potential plane. 4, watch it now. Notice they are seeking a lower potential plane, just as my energy is running downhill now as I do this show. 4. 5 up. 5. And so we say, without question, the momentum before the collision is equal to the momentum after. Consider another classical demonstration of mine, which is easy to do and quite dramatic. Here is a steel pipe. This demonstration I will call virtual, V-I-R-T-U-A-L. There are some demonstrations that I do for real, and I call them real demonstrations. This one we will imagine, and imagination is a very necessary ingredient of this business. We will imagine a steel pipe closed up tightly on one end with a cap, mounted on wheels, and in this chamber I put some dry ice, solid CO2. Then with a wooden plug, I plug it up very firmly, and I let it stand here on the table in the hot air of the classroom or the TV studio, and what happens? The CO2 sublimes, goes into gas or vapor. The pressure builds up more and more. The pressure gets enormous inside. Something has to go. What goes? The cap, with an enormous velocity, enough indeed to kill a man. So if you should do this, I warn you, have some caution. And what happens to the vehicle? It goes the other way. Big mass, little velocity, little mass, large velocity. Conservation of linear momentum. Powerful business, powerful. Consider toys have a large role in my business because the physics of toys is an enchanting thing to engage in. Toys, I would have you understand, ladies and gentlemen and boys and girls, toys are intended for child's play, but the physics of them is hardly that. Here is a little propeller with some inclined blades, and I have mounted it in a chamber wherein resides a spring. So I am storing some wound-up elastic energy in the spring, and I release it. I did that one prematurely. What happens? How is Newton's third law? How does it play a role here? Answer. The pitched blade engages the air, drives the air down with a momentum mv. The vehicle must go up. Watch it. There it is. Oh, that's a pretty thing. And then it's spinning as a top, about which I will speak in another program. So the question to be asked is, how does a bird fly? Here is a bird flying. Here is a bird. I'm probably viewed as a vulture. Bird. I can only fly if I push the air down, and that's why I go up. Now, when a bird soars, as they do ever so gracefully, that is quite another thing, again, to be considered subsequently. Or a balloon. Here's a balloon. Incidentally, I'm going to do a program on bubbles and the like, and I will raise the question of why is it hardest to blow up a balloon at the very beginning and easier to blow it up the bigger you get it. But anyway, I've put some air in there. Now you know if I let the air out here, momentum mv, momentum the other way. There it is, like that. And one last exploration. Hero's engine. Here is a little vehicle you can make out of a tin can. You put some tubes through it and bend the tubes at right angles to their lengths. Put some water in here. Boil the water. The steam, more exactly vapor, which becomes steam on condensation, the vapor comes out the orifices, and this turns around ever so fast. This is a substantial demonstration of Newton's third law. And here is a bigger scale one on which we could run a very quantitative experiment. So much water, so much heat energy put in, so much energy gotten in the angular velocity of the vehicle. And so, what must we now say? We have explored in the passing shows the first law in two parts, the second law, which is wrapped up in F equals ma, and the third law, referred to as action and reaction, which I will close in this way. Here is a very freewheeling vehicle, and you know that if I stand on it at rest and go forward, the cart must go backward, which it does. And I say that when I walk this way, the earth goes the other way. I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And on today's program, our special business is the subject of energy and momentum, two of the great immutable ideas of physics, and we must make clear their difference. So, for my purpose, I go to the two cars again. You remember what we have in earlier programs: a large, massive car on wheels, and a smaller car, little m, on wheels, and they are on the tabletop, and they are connected by a sort of elastic connection of rubber bands. Now, when I pull them apart, I store some elastic energy in the stretch spring, and there is a force then which is exerted on both cars. Now, what did we learn before? We learned that the big car has a little acceleration and the little car a big acceleration because one and the same force acts on both cars. Now, we also saw on another occasion that the little car acquired the greater velocity and the bigger car the lesser velocity, and we called the product of m and v the momentum. And it is not unreasonable now to say that because the accelerations are inversely as the masses, the velocities are so, and therefore the momentum of the little car is equal to the momentum of the big car. So their momenta are equal. But now watch. Is it not true that the smaller car went the greater distance? That is, if I let them come from a place of rest and meet, they would meet somewhere in here. This is the distance the big car would go, and this is the distance the little car would go. So the little car goes the greater distance, s, little s. And now I define for you what is meant by work or energy in physics. The product of a force and a distance. The product of a force and a distance. So, the same force acts on both cars, but for the big car, the distance is a little one, and for the little car, the distance is a big one. And these products are not equal. So we learn this astonishing thing, that although the forces are the same, the accelerations are inversely as the masses, the distances are inversely as the masses, the momenta are equal, but the energies are not. Very important idea. Now this business of energy, beautifully demonstrated as follows. Look what we have here. Here is a curved track, straight and short here, straight and long here. Now this end of the track is at the very same elevation above the tabletop as this end. I have shimmed it up on that end to get it horizontal. And what do? We put a ball at the top of this track at this end. It has so much potential energy, being so high above the zero potential plane, and I let it go. Now it is losing some of its potential energy, gaining kinetic, losing energy really because friction is in the system, and we hear sound, which costs the ball something. It cannot produce the acoustic energy for nothing. Now what do some think? That coming down this long track, the ball down here will have enough velocity, enough kinetic energy of motion to put it up over the track here. But that is not so. If the system were absolutely ideal, no friction at all, which is impossible, the best the ball could ever do would be to go to the same height here. And since we are in a real world and friction plays a large role, the ball can never go as high on that end as I let it go from on this end. Watch it. Oh, it did. I'm glad it did, because I said it wouldn't. So somebody says, Professor, the experiment failed. No, I think what I have done, I manipulated this end a little improperly so that this end is higher, and therefore it did what it did. So you see, a lesson to be learned. Experiments never fail. I'm going to lower this a little, and now I hope that this end is the same height as that. Now watch it. Oh, that's it. And less, and less, and less, and less, and less, and so on until the energy of the system is spent in friction and in producing sound and in vibration. A very beautiful demonstration a device which I call my energy track. Now, let's consider this business of energy further. Here is a block of wood. Here is a nail. I drive the nail into the block of wood. Oh, says somebody, what kind of physics is that? Astonishing physics. Why? I am doing work on the nail. The nail is doing work on the wood to separate its particles. And when work is done, when it is done against friction forces, heat energy always arises. Heat is a necessary consequence of work done against friction. Proof. I'm going to pull that out. Oh, what do I feel? Too hot to handle. Accordingly, the work I did on the nail has been commuted to friction. Now, there are several kinds of energy. Several kinds which we need to consider. Mechanical energy. Mechanical energy. Thermal energy. I just showed you that with the nail heated by driving it in. While we're talking about thermal energy, here is some popcorn. Some popcorn. Now you know that if you apply thermal energy to the popcorn, it soon, as a result of this application of thermal energy, of heat, explodes. Why? Because we gave energy to the little bit of water in the droplet, in the kernel of corn. It expanded enormously. How many times does it expand? Fantastic. 1,700 times. Isn't that fantastic? No wonder the kernel explodes with a rupturing force. Mechanical energy, thermal energy, acoustic energy. Sure, my vocal cords are in vibration, and that's the only reason you can hear me. I am giving rise to excitation of the air in this place, and it is falling on your eardrum and putting your eardrum into motion, and then the bones in the ear, and finally the impulse gets to your brain. Acoustic. Magnetic energy. Electrostatic energy. Electrostatic. Let me show you that, because it is absolutely exciting. Watch this. Watch. I have here some cork dust, which I put out on the table. Cork dust. It is lifeless and dead and inert. Here is a Bakelite hard rubber rod. Now the rod, I say, and later we will say more about it on a program on electrostatics, the rod is electrostatically neutral. I bring it near the cork dust, and what do I see happen? Answer, nothing. Seeing nothing happens is a very important thing to see. Very important. Now I am going to do some work on this rubber rod. Work, work. Now watch. Oh, mamma mia, look at that. The cork dust has been attracted to the rod. Not only that, but it's jumping off. It's jumping off. Oh, and would you believe it? This is the foundation of all of our electric science. Indeed, these television cameras could not work were this principle not uncovered. More about energy. More energy. Energy. Here is a massive weight which I have lifted above the level of the floor, the zero potential plane. I am doing some mechanical work on it. I am endowing it with potential energy. Here is a nail in a block of wood, and I release the weight. Look what has happened. It has driven the nail into the block. The heat developed here, very substantial. A toy, energy, a toy, a spring. If I do work on the spring, I store energy in the spring. There is a so-called suction cup on the bottom, and in another program I will show you that that word suction is not a good one ever to use, but I'm going to put a ball in this upper platform, push down the spring, storing some energy in the compressed spring. Now the energy is available to do work for me on the ball. When the atmospheric pressure seeps into that so-called suction cup, it will let the spring loose, and you know the consequence. Up will go the ball. There it goes. Up went the ball. And there was something else. There was some action taking place in this projectile mechanism which bears also on momentum and energy. Consider this business of momentum. This gun is a toy, and so we need have no fear about it, but don't play with guns. Concerning momentum, if I shoot the gun holding it far from my shoulder, will it not kick very severely and hurt me? Why? The mass of the gun recoils with a certain velocity, the M and the V constituting a certain momentum. How do you avoid this kick? You hold the gun tightly against your shoulder so that when the gun recoils, you and the gun constitute a larger mass and therefore less recoil velocity. An excellent demonstration of momentum conservation. Consider a toy made for 3-year-olds. Here is a little toy, a teddy bear mounted on an elastic shaft through his shoulders. He stands in a vertical plane because his center of gravity is below his axis of support. And now what am I going to do? I rolled him away, and he rolls back. And so I am demonstrating a profound principle of physics in a toy for 2-year-olds. We stored some elastic energy. It was now available to do work on me to return the car. Or such a toy, an array of geared wheels and a shaft, and some feelers in there which rub against other things and produce heat from friction. And notice, I am showing the transmutation of mechanical work into thermal energy as well as into light, because when bodies get hot enough, they become incandescent. Energy, momentum, very important. Now, as one views the history of this subject, I invite you to study it yourself, because for 150 years there was much dispute on the difference between mv and mv square, which was settled by a Frenchman named D'Alembert. But who gave rise to the problem in the first place? A young Dutchman by the name of Christian Huygens. And I want to show you a picture of him as a little boy at the age of 11, an enchanting little rascal. And I shall have more to say about him sometime on a program on light, because he spent his youthful days throwing pebbles into the canals in his native Holland and watching the ever-growing circles of disturbance, and thus was led to the idea of the wave motion of light. And here, finally, is a picture of him in his later days with his what shall we call it, wig. Now, the idea of momentum must be clearly distinguished from the idea of energy. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the subject of freely falling bodies and bodies which are projected, projectile motion. And I would remind you of things already learned in earlier lessons, such as, for example, a body of small mass, a body of enormous mass, released to fall freely, released simultaneously to fall freely. And what is their behavior? They fall at the same rate. And you remember, it is Newton's second law that tells us that, namely that F equals ma, or for freely falling bodies, W equals mg. Now, what is the action of a body falling freely? Of course, it encounters in real life some viscosity and friction and trouble with the atmosphere, So what we can do is lodge a heavy body and a light one, say a coin and a piece of paper, in a tube, and then with a vacuum pump, take out as much air as we can, and then do as follows, and we would see both bodies fall at the same rate. I had this tube originally evacuated, but there has been a leak, so the experiment, as some would say, has failed, but I remind you, I have not provided nature with her requirements to show the simultaneity of fall of both bodies in free space. Now, when we study a falling body, dropped so like that, we learn as follows. Supposing it starts right there. 1 second elapses, and we find it right there. How far has it fallen? 16 feet. Now we let another second elapse, and I'm not drawing this to scale. And how far would it fall in the second second? During the second second, it would fall 48 feet. Now let it fall for a third second. And how far would it fall during the third second? And we find 80 feet. And these numbers have some mathematical enchantment, because 16 divided by 16, 48 divided by 16, 80 divided by 16, and we see that the numbers are the odd numbers beginning with unity, which is a discovery that Galileo made in the 16th century. Now, further than that, you see that the first 2 seconds is 64 feet, the first second is 16 feet, the first 3 seconds is 144 feet, and look at these numbers. 16 into 64 is 4, that's 2 squared. 16 into 144 is 9, that's 3 squared. So the distances all fallen during the succeeding seconds are in the order 1, 4, 9. You see, 1, 4, 9. 1 squared, 2 squared, 3 squared. Now, when we study a freely falling body, it is too far to measure in real life. So what do? We have a machine which records a falling body and where it is every 60th of a second. And here is a tape which I have run, and the point to be noticed is that the distances as we go down increase in the order I have described, a discovery made by Galileo. Now, there is another exciting adventure regarding falling bodies. Another very exciting adventure. Supposing I had a body A and a body B on the same horizontal level with respect to the ground. And what am I going to do? I'm going to allow A to fall freely, and B, I'm going to project horizontally, like that. Now, you know the path it takes is a parabola. Indeed, this was discovered also by Galileo in the 16th century. And the question that's enchanting is this: how about their times of arrival at the ground? The impulsive notion is, well, this is going much farther and hence should take longer. But that is not true. The time of fall for A to the ground and B to the ground are one and the same. Why? Because the horizontal velocity of B remains unaltered, and the vertical velocity is taken care of by gravitational forces, the same in both cases. And here we have an experiment, a demonstration to show that. Here is a device with a spring which permits me to shoot a ball horizontally, as in the case of B, and here is one that I can release to fall freely, as A in the picture, and we will rely on our senses, hearing and sight, to verify what happens. Watch it. Simultaneity of impact. Now, this is not a proof, but it is a suggestion of the reliability of the law of falling bodies and projectiles. Consider now another one. This one has absolute enchantment. Let me put a ball in a car on a spring. And now I will put the spring in compression, drive the car away from me. The spring will be released and project the ball vertically, and the car will go horizontally, and it does no longer have the ball in it. Pretty soon the car is over here. And what do we discover? We discover an amazing and wonderful thing, that the ball is caught by the car. And I'm going to show you that. First, let us take a look at the mechanism. here is the cart, there is the ball, and I have compressed the spring, and it is held by a pin below. So when I pull a string, which releases the spring, the ball will be shot up. Let's get over to this table and take a look at it. I'll put something down out of the way here. Let us take a look at it. Watch now, watch. I am going to drive the car away. So, pull the pin, up goes the ball, the car keeps going, and zowie, the ball is caught by the car. Watch it now. There it is. Now, I did not go so very high, and perhaps I should do that again to show you what a wonderful thing it is to witness. Watch it. Watch it. Oh, this is... There it is. And I say, this is enchanting to witness, which suggests a very important piece of physics. The horizontal motion of the car, which we would refer to as V horizontal, the horizontal velocity, is independent of the vertical velocity. Each goes its own way without interference by the other. Now, here is an experiment that I wish to talk about, but will not show you, and I suggest you try to make the apparatus yourself. I call it the monkey and hunter. Here it is. Let us take a tube, say of lucite, such as I have here, and let us bore sight on a monkey here. That's why I call it a monkey and hunter. Now, what is the monkey going to be? The monkey is going to be a tin can held up by an electromagnet. Now what am I going to do? I'm going to put a light, say a lucite ball, in this place here, in the chamber of the gun, and I'm going to have two little wires across the end of this tube, such as I have right here. If you look carefully, I'll take that stopper out. Now, what happens? When these two wires are crossed, the electromagnetic circuit is closed and the tin can is held up. Now I put my mouth to this end in this fashion, and I blow. Now you know what happens. The projectile emerges here. As it emerges, it opens the two little wires. The electromagnet loses its magnetic hold, and the monkey falls down. There's the monkey. Now let's say the monkey falls to there in a certain time. And what do we expect? We expect the projectile to hit him. And here is a very important detail. The monkey can never be hit at that place if he stays there. Why? Because the moment the projectile emerges, it is taken down by gravitational forces and can never hit the monkey. That is to say, looking at it in another view, that if we had a gun aimed absolutely horizontally at a target on the nose, and we fired the gun absolutely horizontally, and the projectile emerged there, we could never hit the bullseye. Never. Why? Because the instant the projectile emerges, it is taken down like that. And as an illustration of numbers, supposing the muzzle velocity of the gun was 1,000 feet per second. 1,000 feet per second. Supposing this was 1,000 feet. And supposing under ideal conditions the horizontal velocity of the projectile remains unaltered, it would take 1 second for the projectile to reach the target. But in 1 second, how far do gravitational forces take the projectile? As we discovered, 16 feet. Now somebody says, look here, Professor, I shoot guns and I hit targets. Of course you do, because what is really done is this. The sight on the gun is such as to compensate for this fall due to gravitational forces, and so the projectile is hit. So, remember, it is Newton and Galileo, very important in the case of falling bodies and projectile motion. Now, here is another experiment that you can do. Did we not say that when a body falls from rest, it falls successively farther. And the distance is 16 feet, 48 feet, 80 feet, and so on. I have here another experiment that you can do. And we need to take a look at an apparatus which you can make at home. It consists of a string to which are attached some spheres. And I have used billiard balls. And now, since this is pretty high, I will show you that at the bottom, the separation is closer and farther apart as we get higher. So the picture I have drawn on the blackboard is turned upside down. Now, supposing we release the whole string of things from the very top, would not the successive impacts of these balls on the ground be in arithmetic progression? Every second, let us say, one would hit, or every certain part of a second, but the distances are clearly in geometric proportion, as you see from what I have done on the blackboard. Very exciting adventures. And I must say again, this business of 1, 3, 5, uncovered by Galileo, and remember, this distance is 16 feet in the first second, in the first 2 seconds, 64 feet, in the first 3 seconds, 144 feet, and I wish to point out again, because this is enchanting to follow, this number, if we divide by 16 is 1, if we divide by 16 is 4, if we divide by 16 is 9, and you see 1 is 1 squared, and 4 is 2 squared, and 9 is 3 squared. So to quote Galileo, the distances passed over by a falling body beginning at 0 time are in the ratio of the odd numbers beginning with 1, 1, 3, 5. But the total distances passed over, 16, 64, 144, are in the ratio of the integers beginning with 1 squared. 1 squared, 2 squared, 3 squared, and so the next must be, of course, 4 squared, and so on. And since I have spoken about Galileo, we should take a look at this wondrous gentleman of Florence and Pisa and Rome and Padua. And here is Galileo, 1564, 1642. And I thank you for attending to our business. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today has uncommon enchantment because the motion is beautiful to witness and wonderful to understand. We are going to talk about simple pendulums and other oscillating things. Consider the following. If we have a rigid support, and there are none really because everyone shakes however rigid, and we hang an ideal string. By an ideal string, I mean a string that has no mass, no weight, has no inertia, has no tension, is perfectly inelastic, ideal mathematically, and we hang a small bob on the end, and we displace it from this equilibrium position and let it go. It oscillates as a simple pendulum. Now, we wish to explore its motion. When you study the lesson in this business, you will find that the period, which is the time for a complete trip, comes out to be some such expression with which I will not have much to say, about which I will not have much to say. It's governed, as we see, by the square root of the length and depends upon where we time it. You know, for example, that g is one thing on the Earth and quite another thing on the moon. G is 32 feet per second on the Earth, but about 1/6 of that on the moon. as an incidental matter, you would weigh, therefore, 1/6 as much on the moon as you weigh on the Earth. Now, I wish to do another pretty experiment with several pendulums. And I suppose maybe we could say pendula. This may be the plural of pendulum. Now, what am I going to do? I am going to hang up 3 of them, as I have them here soon to witness. 1, 2, 3. And how long are they going to be? This one is going to be 10 centimeters long, and this one 40 centimeters long, and this one 90 centimeters long. So the lengths are 10, 40, 90 centimeters. Notice the numbers, 10, 40, 90. I hope you get a little Q in there. There's 1, there's 4, there's 9, if we divide each one by 10. Now I am going to set them into oscillation. And I am going to count, say, 20 vibrations of each one. Here's the way I would do it. I would set this one into vibration, starting with 0, and here is a clock which I would start and stop, and I will just run one a moment to give you the cue. I would remind you parenthetically, I am not really giving you a lecture in physics. I am merely pointing out some things that you yourself can do with your teacher and even at home, and my purpose is singularly this, to invite your interest and stir your enthusiasm and curiosity, and point up at the same time the beauty and drama in these things. So I would start this 0, 0, 1, 2, 3, 4, and I would count 20 oscillations. And what would I get, probably, in this laboratory? I would get about 13 seconds. Now, where you are, say Colorado on a high mountain, you would get a different time. And if you were in Australia, you would get a different time, because little g is different from place to place on the Earth. So I count 20 oscillations, and I get 13 seconds. Now I do it all over with this one. And I count 20 oscillations. And what would I get? I would get about 26 seconds. You thinking of something? Then I would do it with the 90 centimeter one. 0, 1. Oh, I should have stopped this thing because I'm not really clocking. What's going on here? Huh. Well, there's something wrong with the... Notice now, this is the hazard we run when we depend on mechanical things. So I'm going to put the clock out of my sight. What would I do? Coming back here, somebody says, isn't the professor having a wonderful time with things going wrong? Sure they are. When you deal with nature, you must make her requirements absolutely perfect, or she will not do what you want done. So I count. I count 20 oscillations, and lo and behold, I get 39 seconds. Look, 10, 40, 90. They are in the ratio of 1 to 4 to 9. 13, 26, 39. They are in the ratio of 1 to 2 to 3. And now a marvelous thing is encountered. 1 is the square root of 1, 2 is the square root of 4, and 3 is the square root of 9. And that's what that so-called formula says, that the period is proportional to the square root of the length. And this other stuff comes out of some mathematical gymnastic. So we have learned a wonderful thing about pendulums by examining the motion of 3 of them. Now, strangely enough, when you make the exploration or develop the formula mathematically, notice that it does not contain, it says nothing about how big is the pendulum bob, how massive is it. All the period depends upon is its length. And you can show this by such an adventure as I have here. Here I have some pendula which are of identical length, let us say. Here is one made of brass, there is one of aluminum, there is one of cork, and we would find that if their lengths are identical, then their periods are identical. And that's a wonderful thing, because wouldn't you think that the heavier the bob, a different period would result? No, it does not. So we deal with simple pendula, pendulums, a bob on the end of a string. Now, anything can be a simple pendulum. Anything. Let me illustrate. Supposing you took me here, there I am, and you put a hook there in me, and you oscillated me. I am a pendulum, but not a simple one. I am a complex one. Or better physics language, I am a physical pendulum. A physical pendulum. And what is a physical pendulum? Anything that is not a simple pendulum. Illustration. Here is a metal rod. Now, if I put this on a support at one end and I oscillate it in a vertical plane, it has a certain period. It has a certain period. Now, remember, if it has a certain period, about an axis through one end, it has a certain time for its oscillation. Must there not be a simple pendulum which has the same period? Yes, indeed. A simple pendulum has the same period if it is so long. Now, how long is the simple pendulum that has the same period as this rod? Wonderful. If this rod is length L, the equivalent simple pendulum is 2/3 of L. So if I had a simple pendulum hanging here in this fashion, which was 2/3 as long as the rod, and I put them into oscillation together, they would stay in phase, meaning that they would keep step in step. So we speak of the equivalent simple pendulum as a simple pendulum which has the same period as the physical pendulum. Now, this is a rod, and this has a marvelous property. If I turn it around and put the axis at the 2/3 mark, and I oscillate it, it would be looking like this, of course, now. Here is the 2/3 mark. Here is a remarkable thing, absolutely enchanting. This rod has the same period for this axis as for this one. The same period. And hardly anybody ever believes that. But it is true, as you can discover by doing the experiment yourself. So now we explored a physical pendulum, which is a rod. How about a hoop? Here is a hoop. I have here a hoop, and I could support it by an axis about one edge, and I could let it oscillate in a vertical plane. I could let it oscillate in a vertical plane. Does it not have a certain period? Of course. It therefore has an equivalent simple pendulum. And how long is the equivalent simple pendulum? It is a marvelous thing to discover, but the equivalent simple pendulum has a length equal to the diameter of the hoop. So if you put a simple pendulum up here, which has this diameter, this length, they would keep in phase. Finally, how about a disc? Oh, a disc. Here is a uniform circular plate. And could I not support it on an axis in the manner as before and let it swing in its own plane? Supposing, well, I better draw a new picture. We are talking about a circular disc, a uniform circular plate, and I oscillated about one edge. What is the equivalent simple pendulum? Strangely enough, the equivalent simple pendulum is 3/4 of the diameter, a matter which you can explore by making some of these things yourself. Now, in addition to simple pendula, that's a bob on a string, and physical pendula, which are bodies of any shape, like rods and discs and hoops and the like, there are many other oscillating devices. Consider, for example, a spring. Here is a beautiful spring, nicely wound, so long when unloaded. I put a load on it, and I call your attention to the beautiful motion which it executes. That has a certain period in terms of the property of the spring. Now supposing I put a heavier load on it. a heavier load. Watch it. And I say that's a beautiful motion to experience, to witness. And now, the question, a beautiful question. Here is a spring of certain length and so stiff. Here is an identical spring which is only half as long. The question which arises is this. If the motion of this pendulum is so much with a certain load, what would be the motion of half the spring with the same load? And it is a wonderful thing to discover that it has, well, I'm not going to say. I'll leave it as something for you to explore, because I think it has much more virtue to leave some questions unanswered for you to explore than to just give you the answer. So I suggest you get a spring, indeed 2 springs, and explore their motions when one is twice as long as the other. And indeed you will notice that I have coupled springs in different ways, suggesting that their periodic motions depend upon how they are coupled. Regarding coupled pendula, look here. Here I have a pendulum, a heavy lead bob on the end of a rod, which is pretty nearly a simple pendulum. And here is another one. And I have, as we say, coupled them by putting a spring between them. And watch the marvelous behavior. I'm going to start one. I'm going to start one and let it swing. And we will see this enchantment. Its motion will soon die out, and the other one will take up the motion. Then that one will die out, and the other one will take up the motion. And this coupling of pendulums has much to do with electric circuits, about which we shall talk another time. But watch it. This one is going. That one is going more. Watch this one stop. That has practically stopped. Now this one is going to stop. It has practically stopped, and this one is going. And so we speak of coupled harmonic oscillators. Here is another pair. Here are 2 weights on very flexible rods. If I start one, we will discover a wonderful thing, that the motion of the first one is arrested and the energy is taken up by the second one. So, I urge you to explore the behavior of oscillating bodies, and I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And my business today has most uncommon enchantment. And of all the things I like to do, of which there are hundreds in this business of demonstrations, this indeed enchants my soul the most. It has to do with the principle of Bernoulli. Bernoulli. B-E-R-N-O-U-L-L-I. And I urge you to go and read about the Bernoullis, because they were an uncommon family. 120 of them, all geniuses, unlike anything in the history of the humankind. The best that we've ever had are the Bachs in music, and there were only at most 24 of those. But can you imagine over 100 people named Bernoulli, all geniuses, not one an ordinary man? Now I will recite to you quickly and passingly the principles lying herein these demonstrations, which you can read about in your books. First, we learn from Bernoulli that when a moving fluid like air encounters a constriction, that is a narrow space, the velocity increases. So as we say, the velocity is increased in a constriction. One other principle emerges from a study of Bernoulli, and that is that the pressure in a constriction diminishes, or goes down. So we have these two principles. Velocity increases, pressure diminishes in a constriction. And now I'm going to show you an abundance, an array of experiments, demonstrations that reveal this. Consider the following. Why an airplane can fly, says Bernoulli. He explains why. Why a ball can be thrown in a curve. Why a chimney has a good draft. Why a bird can soar. Why a boomerang, whatever it does, boomerangs. All of these things can be accounted for in terms of Bernoulli's principle. Here is a magazine opened so that the pages are curved in this way. And now I'm going to blow a stream of air against the inner edge of these pages. One would think that they would be pushed down by the push of the air. But no, watch. Watch. Well, the page was lifted up. There it is. Now that airplane wing has some flutter, which we don't want, of course, in a real airplane wing. But the air going over the top gave rise to a diminution in pressure, and the atmosphere below lifted the page up. Consider another of the same. Here are two spheres, two croquet balls, with a little separation between them, and this region is a constriction. I'm going to blow some air through there. One would think impulsively that the spheres will be blown apart. No, they are not. The pressure will be reduced and the atmosphere will push them together. Watch it. There they are, pushed together by the greater atmospheric pressure on the outside. Now, of what consequence is this? Well, very important indeed, because if two ships pass, let us say, two ships passing on the sea, if they pass too close to one another, the pressure is reduced between them and they could be made to collide and break apart. Here is another, very dramatic, my chimney effect. Here I have a chimney. You remember a requirement of our work together is imagination. So I could, of course, draw the picture of my house and my chimney, and there's the fireplace in my house. Now, why does my chimney have a good draft? It has a good draft if there is a stout wind blowing across the top of the chimney. Why? Because high velocity, diminution in pressure, the atmospheric pressure pushes the smoke up the chimney. I'm going to prove that. Here is my fireplace. My fireplace is a vessel with some puffed rice. Here is the chimney. I'm going to blow a sharp stream of air across the top. The pressure will be reduced here in this region. The reduction in pressure will be felt in the tube, and the atmosphere will push it up. Watch it. There it is. My chimney has an extraordinarily good draft. Watch it. There it is. I say that's a terrific chimney. Now, here's one that's even better still. Here's a funnel. And I'm going to put some puffed rice in that funnel. And then I'm going to blow some air through that funnel just to show you that air is blowing out of that funnel. Watch it now. Whoop. Oh, well, of course, there it is. Sure, the puffed rice couldn't have come out unless I blew it out. Now I'm going to put a ping pong ball in there. There it is. Now I'm going to blow that ping pong ball out. Watch it. Indeed. Somebody says, oh, he's got it stuck in there by magnets or something. No, no. I will dispose of it as quickly as I can with the following remark. Here it is. Here it is. Here is the funnel. There is the ball. Here is the air. The ball fits in the funnel very snugly, and these regions right here are constrictions, and when the air passes in there, it has a high velocity and a reduction in pressure, and the atmosphere holds the ball up. Indeed, this principle of Bernoulli is why an atomizer works. You know what an atomizer is. An atomizer is a tube that resides in a vessel, and here is some liquid, and here is a tube across here, and here is a bulb, and you squeeze the bulb, air rushes across, there is a reduction in pressure, the atmosphere pushes the liquid up, and then the liquid is caught in the airstream and comes out there. I have often thought that the reason that's called an atomizer is because little atoms of the liquid come out there. Don't you like that idea, little atoms? Now, here is an atomizer, and spray would come out there. Now, I'm going to show you an atomizer on large scale. Watch it. This is fantastic. Here is a tin can, and here is a tube quite like that one residing in the atomizer. And I'm going to blow a stream of air through this tube. There will be a reduction of pressure in the tin can. And now what will the atmosphere do if the can has less pressure inside? The atmosphere will collapse it because it is enormously strong. Watch it. Watch. There it is. There it is. I tell you, that's terrific. It's so terrific, I'm going to do it again with another one. With another one. Yeah. Why? Well, if I like it, I'm going to do it twice. I may do it 3, 4 times. Watch it. Oh, look at that. Well, that's 2 times, and I'm going to do it once more. Once more. Why? Because I like it. Watch. Whoop, whoop. Whoop. Oh, well, there it is. Notice, there it is. Wait. There it is. There it is. And I tell you, that's terrific. That's fantastic. Now, pressure reduced in a constriction, velocity increased. Consider a consequence. Flag. United States flag, Australian flag. Why does a flag flutter? Bernoulli. Have you not heard sometimes your Venetian blinds chatter? Bernoulli. The air blowing across the top of the shutter gives rise to a reduction in pressure. The shutter is lifted up. Now, because of its springiness and its inertia, it falls back, and so it oscillates. And I'll tell you how powerful an instrument Bernoulli's principle is. Some years ago, a bridge way up in northern Washington collapsed because of the effect of Bernoulli's principle, because of the role Bernoulli played. Now we got something wonderful. Terrific. Oh, why is it terrific? Because you would not believe it. Here it is. Supposing I had a tube, and I drove a stream of air up here, and I had a ball right at the top, vertically above the blowing air. You would say if the ball stays there, it's because the air pushes up and the ball pushes down, and when they are equal, the ball stays there. And that would be correct. But now supposing I turned the tube off the vertical, and the ball still stayed there. Well, you can't say that anymore, because when the ball receives the air that way, there is a component that way and a component that way. That one may hold up the ball, but this one should drive it away. But I'm going to show you that it doesn't. Watch it. Oh, oh, little trouble. Uh-oh. Let me try a heavier ball, a golf ball. And I call to your attention a very significant feature of this. The ball was spinning. This spin gave rise to a reduction of pressure on the upper side, whereupon the atmosphere held it up. Let's take a big one like this. Styrofoam ball. Watch it. I hope we have air enough. Watch. And I say that's terrific. I just love that. I want to do it again because I do. Any objections notwithstanding. Question, could I get that ball on the horizontal? That's a good one to explore. Indeed, you can do this by going to your gasoline station and using the air hose at your service station. Let me do it again with a golf ball, which is quite heavy. Golf ball, quite heavy. Oops, little trouble. Finally, since I enjoy, as you know, the physics in toys, here is a wonderful demonstration of Bernoulli. Here is a little toy car. Here is a little toy car. And what am I doing? I am storing some energy in a wound-up spring, and when I release the spring, it unwinds and turns a fan, and there is a stream of air emerging from here. I'm going to show you that there is. Watch it. There is a little polystyrene ball. There it is. Now remember, I can put that off the vertical. Watch it. There it is. Now what I'm going to do should be an enchantment for ages 4 to 94, as all the physics that we do should be. Watch it now. Watch. Oh, isn't that something? Look at that. I want to do that again because I like it. There it is. This is a Bernoulli car, and why does it work as it does? Because, one, there is a push of the air, a high velocity on one side of the ball, which gives rise to a diminution in pressure, and thereby the atmospheric below holds it up. Now, what shall we say about Bernoulli? The applications are phenomenal. As I've remarked, two ships passing on the sea should not pass too close to each other. Indeed, have you not stood on the sidewalk when a fast-moving vehicle has gone by and you have been made to rock? Or have you not passed in your car, a bus, let us say, and your car is made to rock? This is a consequence of the reduction in pressure between the vehicles, whereupon the atmosphere on the outside pushes them together. Indeed, when the Japanese designed their most recently accomplished railroad from Osaka to Tokyo, where the trains go about 120 miles an hour, what was the critical thing? Several. One, the center of gravity idea. Number two, how close can the cars be without the effect of Bernoulli? And so I say, read about the Bernoullis. They are wonderful to know about. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business, and the physics today has uncommon enchantment and beauty. It has to do with soap bubbles and soap films and surface tension and why raindrops are round and other such enchanting matters. Let me do now, first on the blackboard, some introduction to the first experiment, which you will be enchanted by, I am sure. Let us consider a T-tube, so, with an arm here, and a little funnel or thistle tube there, and a thistle tube here, and let's say a rubber tube there, so I can blow some air in here by mouth. Now I am going to dip the ends of these funnels into some soap solution and blow some bubbles. So you see what has come to me in my 58th year, an old man, a physicist, playing with soap bubbles. But I have spent 40 years playing with soap bubbles and have not yet tired of it. So I'm going to blow two bubbles. Now I could blow two bubbles, both the same size, but there would be no interest in that because there'd be no problem. I like to pose problems. So I am going to blow a small bubble on this side and a big one on this side. S for small and B for big. And I can do that because some of the tubing here is flexible and I can shut it off and blow more air into that one than into this one. Now, having blown the two bubbles, I close off this connection with the outside atmosphere. So the bubbles are connected with each other, but not with the outside air. And the logical question that must be asked is this: what now happens? And invariably, everybody says, well, they get equal, because there's more stuff in here that comes over here, and when they get equal, there's the same stuff in both, and then they stay equal. But this is not so. It turns out that the smaller bubble blows the bigger one bigger. As one student once said to me, it looks, Professor, as them that has gets, which is a very good expression of it. Why does this happen? Well, the fact remains that the pressure in the smaller bubble is greater than in the bigger bubble, which ravages reason. Now let me do this. I have here the two little funnels, and here is a soap solution, and there is soap. And I squeeze here. And now I shut off the connection with the outside air, and watch the smaller bubble get smaller. Watch it. We're a little twisted there. Watch it. Look at it. Look at it. And not only does it get smaller, but the smaller it gets, the faster it gets smaller. Watch it. Watch it. Watch it. Watch it. Look at that. Look at that. I'm going to blow it again. Watch it now. And I would call your attention to the beautiful colors in the soap bubbles, which has to do with the colors. There it is. Look at it, getting smaller and smaller, smaller. And this is well, it's incredible that the smaller bubble should blow the bigger one bigger. And for those of you who are equipped with the mathematics, the pressure is inversely as the radius of the bubble. So we are dealing here with pressures in bubbles. 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 B-U-B-B-L-E-S. Now, bubbles is one kind of business, and drops are quite another. So I'm going to show you some wonderful experiments, first with surface tension on a liquid, and then on the shape of droplets. Consider the following. I have here a little paper cup, which already has some water in it, and I'm going to pour more water into it. More water. More water. And I hope you see that the surface is quite rounded up, quite much higher than the cup. Look at that. Isn't that incredible? Incredible. Notice how much above the cup that surface of the liquid is. Indeed, let me go back and make a comment about that. I have sometimes had a vessel filled with water so that it overhangs like that. And this surface film has great tenacity. Indeed, have you not seen little bugs flitter about on the surface of a quiet pool of water without getting their feet wet? Now, I'm going to show you that on this high elevated surface of water, the membrane surface is so tight that I can float steel on it. And here is a needle which is steel. And I'm going to try to drop it on there and hope to show you that steel can float on water. Watch it now. I must be very careful because I may puncture the surface film and it'll sink. There it is, there it is. Oh, man, am I delighted. There is the needle floating on the water. Steel floating on water, which shows you the tremendous tenacity. Now I spoke about droplets. Here I have some mercury and a medicine dropper, and I am going to take out some mercury and form a drop. And look it, when the drop is small, it is round, spherical. But the bigger it gets, oh, I have a little water mixed up with that, unfortunately. But you notice that the bigger the droplet gets, the flatter it gets. But the point I wish to make here is as follows. Supposing I bring two droplets of mercury close upon each other. Oh, I mixed this with a little water, which spoiled the effect somewhat. But supposing I bring them close upon each other. Watch them, watch them. Oh, look at that. Look at that. Well, as a matter of fact, the fact that I got the mercury a little wet with water has changed the surface tension properties, and it is not doing what I want it to do. Indeed, it is doing just what I don't want it to do, which raises some very exciting questions. But the point I wish to make is that when the drops coalesce, go together, they go together with enormous forces and speed, and this is due to the electrical properties which the liquid possesses. So there we have surface tension, the shape of drops, and the shape and form of bubbles. And while I'm on this, I would suggest to you that there is a paperback book entitled Soap Bubbles and the Forces Which Form Them, written by an English physicist whose name was C.V. Boys, B-O-Y-S, like boys and girls. And I would urge you to read it, because there are hundreds of experiments there you can do with soap solutions, soap bubbles. Now more on the same. Here is a rectangular cubical frame of wire. I'm going to submerge it into the soap solution and withdraw it, and you notice the enchanting shape which we have here. Now, what must physicists say of these shapes? The shape which the soap has taken is a shape of least energy. And you will remember on an earlier program I remarked that the energy of a system tends toward less. So watch what happens when I puncture one frame. Watch. Oh, there it goes, and look at that beautiful shape. And now, there it goes. There it goes. Oh, there's another one. Always tending toward a surface of less energy. Now, why are raindrops round? The reason they are round is that they have the largest volume with the least surface. That's the property of a sphere, and hence their energy in this shape is the least. To show you that a circular or spherical form is always that toward which a system goes, I'm going to dip this ring in some soap, and here is a flexible loop of thread. Now watch what happens. I draw it out, and I have, oh, it's not what I want. I draw it out. Oh, it's not what I want. Oh, well, I'll show it to you. Do you see that the curvature of this thread is circular? Let me try it with another one. I thought I had, oh yes, here's another one. Let me try it, because there are some problems in doing, oh, yeah, this is all right. Now, I'm going to puncture one film and watch the action, the motion of the string. Oh, there it is, into the arc of a circle. So the film above tends by contraction to a least energy. Further proof of this. Here is another ring, and here is a closed loop in here, a closed loop. I'm going to dip this into soap solution, withdraw it very carefully, and you see the loop inside is quite closed because of the tenacious holding of the soap film. Now I'm going to puncture the soap film in that little ring, in that little loop, and you will see it all go into a circular arc. Watch it, watch it. There it is. Now let me do break the film elsewhere in the larger part. Watch it, watch it. There it is, tending toward least energy. I'll do that once more because it's quite enchanting. Watch it. Oh, look at, oh, did you see how tenacious that soap film is? Now watch it. There it is. It goes into the arc of a circle. Here are two loops, side by side, and some interesting things can be done with them. Oh, I'm having a little trouble, and I may abandon it. Yes, let me suggest what you would witness. Let me suggest, because it's very important. Supposing you took a funnel and another funnel, and you dipped their front edges into soap and brought their faces together close and then separated them. What would you have? Well, the film would have that curvature, and that has a very special kind of geometry. That is called a catenary, C-A-T-E-N-A-R-Y, and that's the Latin word for chain. And indeed, if I took a chain here and held one end so and one end so, the curvature of that chain would be a catenary. And it is interesting to discover that in this shape, that film surface has the least energy, which is a fundamental principle of nature, that the energy of a system goes downhill. Now, Since I am interested in blowing soap bubbles, I have here something I'm sure many are familiar with, a little pie plate with some soap solution and a ring, and there I make some bubbles. And I call to your attention their beautiful property. They are spherical. Oh, I thought I could catch that. Watch it now. Oh, I may be a little too impulsive. There it is, there it is. Watch it, watch it, watch it. Oh, I caught it, and it went through the other one, which suggests the tenacity of this business. Look at that. Now, what has this to do with other important matters in nature? I already said that raindrops are spherical, very important. And indeed, may I suggest, if you have a clothesline that hangs from here to here, the next time it rains, I urge you to look carefully at the raindrops that are hanging, the water drops that are hanging. They hang very, very sharply formed and all spherical. And now what do you see happen? These which are in a higher potential level slide downhill. This one hits that one, they coalesce and get bigger, and now the surface tension force is not adequate to hold up this greater weight, and it drops down. So here is a beautiful thing to witness. One last thing. Here is a wedge-shaped vessel, one of which, now held in my right hand, has water in it that is colored with food coloring, and the other has mercury in it. And I hope you see a very distinguishing feature. Let me show you quickly what that feature is. If I have a narrow tube immersed in water, the surface in the water would be so, and the upper surface in the tube would be so. In the mercury, the surface would be so. And this is very important for the affairs of nature, and I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today has more than ordinary enchantment, and I will go at once to it. Consider the following. I have a tin can with some water in it, under which I have put a burner, so that the water has now been boiling for a time, as evidenced by the water vapor seen here condensed, and we call it steam, so that what remains in the vessel now is some water, less than before, and some water vapor. Now I'm going to take the burner away and stopper up the can, and we will witness an astonishing and absolutely astonishing thing. If we listen very carefully, we will hear a certain flexing of the can. What is happening? Some of the water vapor is condensing, the pressure is getting less in the can, and the atmosphere is taking hold. And atmospheric pressure is an astonishing thing. I will hasten the process by pouring some cold water on it. And this is an experiment you can do with absolute enchantment yourself. Here it is. I am going to take the burner away. I am going to stopper this up. I'm going to put it down here. Listen. Oh, but watch it. I'll hasten the process. Oh, there it is. Let me turn it around. There it is. And I say that is something to bear witness to. That is fantastic. The push of the air, staggering in its consequences for the human race. Now listen, listen. The water is boiling inside that can at reduced pressure, at a much lower temperature than 100 degrees centigrade, because the pressure inside is less than 1 atmosphere. This is fantastic. Fantastic. Let me show it to you another way. Here I have another tin can, and I'm going to connect this tin can to a vacuum pump, which permits me to pump out some of the air, and just a little of it. I could never pump it all out. If I pumped for 1,000,000 years, I couldn't get it all out. Why? Too many molecules in there. But let me... There it is. There it is. There it is. The push of the air. Staggering to witness. Staggering. Show it to you another way. Take a look at another piece of apparatus. I have a funnel. A funnel. And across the top of it is a sheet of rubber tubing, as from an automobile inner tubing. The air inside is at atmospheric pressure. I'm going to connect the vacuum pump here and reduce the pressure inside from atmospheric less and less and less and less. And the rubber sheet, suffering the forces, the push of the air, will be depressed inside deeper and deeper and deeper. And indeed, if it can endure the reduction in pressure and the push of the atmosphere, I shall be surprised. Very likely, it will be torn apart. Here it is. There's the rubber tube. I am going to connect this. Now, I'm going to reduce the pressure. There it is, getting pushed in. There it is, getting pushed in. Oh, man, this is something. I'm going to stop it a minute. Let's get a tight shot, if you will, of that. And notice the enormous push of the atmosphere. Fantastic. Now, I'm going to evacuate more and more and let the push of the air push that more and more. And I'm going to step aside because when this does indeed burst, it has a detonation which could, well, unseat this building. That'd be very good. Oh, I like to do this once in a while because it adds to the drama of the matter. It adds to the drama. Oh, there it went. There it went. I hadn't expected it, really. But notice the enormous forces of the air. How enormous? Well, only about 15 pounds per square inch at sea level. Let me remind you of the consequences. The ordinary human being has about 3,000 square inches of surface. 3,000 square inches of surface. 3,000 square inches. If you skinned an ordinary human being, laid out the skin and measured the projected area, it'd be about that. On every square inch, there's about 15 pounds. 45,000 pounds is the push of the air on me. Over 20 tons. Is there any wonder why at the end of the day a fellow goes around all worn out, carrying that load of air? Now, to show you further the consequences, consider these things, which we need to look at sharply, acutely, circumspectly, because what is said about them is always wrong. They are called suction cups. Suction cups. And I must advise you to put the word suction out of your vocabulary. It is unacceptable. Why? Because there is no suction, no such force. What do? Let me squeeze them together, face upon face. And what have I done? I have squeezed the air out from between them. Now, why are they held together? They are held together because of the push of the air. I could compute it very readily. If, let us say, I have squeezed out all the air inside from between them, all I need to do is measure their area. Pi r square is the area of a circle. And that area in square inches times 15 pounds per square inch. Indeed, it turns out that about 300 pounds is necessary to pull these apart. There, about 300 pounds necessary to pull them apart. Of course, look at the usefulness. Look at that. Indeed, regarding the usefulness, the next time you watch people who change big panes of glass in department store windows, you will notice the pane of glass weighs half a ton and 3-4 men carry it. How? By fixing a so-called, forgive me for the use of the language, so-called suction cups, and then they carry it around. The push of the atmosphere. Now, I used a vacuum pump in this, and you should read about Otto von Guericke, Guericke, who in the 16th century invented the vacuum pump. And I want to show you his first one, if we can get a tight shot of that. There we are. Notice, here is a pump with a piston, and two men are drawing on it, and he reports in his report to the societies, the scientific societies, that there was first a slight hissing as by bees and birds, and then bang, the cask collapsed. Here is another one showing the same. Fantastic. Those two hemispheres put together, the original Magdeburg hemispheres. And here is a picture of von Guericke. So we should pay him tribute. We should pay him tribute. Now, I have spoke of the Magdeburg hemispheres. Let's take a look at them. Here they are in replica, two hemispheres made of steel, which I put closely face to face, and then I connect the vacuum pump, and the valve is open, and I take out some of the air. I take out some. Never all, could never take it all out. Then I'm going to close the valve, shut off the pump. Now I'm going to try to pull them apart. Never, not one man alone, indeed two could hardly do it. So I'm going to do something. Obviously, the pressure inside is too low. The push of the atmosphere outside is too big. I'm going to do something. Watch, listen, listen. I'm going to open the valve instantaneously. There. Now what did I do? Oh, some say you let some of the vacuum out. Oh, that murders me. As Macbeth doth murder sleep. Didn't let any of the vacuum out. I let some air in. Still too much. Let more of the vacuum out. Oh. Oh, now I let so much out that all of it's out. And so we have the Magdeburg hemispheres, a classical demonstration historically of atmospheric pressure. One more very dramatic one. On an earlier program, I showed this when I talked about inertia. But I want to do this now because it is a demonstration of atmospheric pressure. You see, ladies and gentlemen and boys and girls, what I'm trying to do is not teach any physics in these recitations, but rather stir your interest by events which are dramatic for the soul. Here is a sheet of paper, about 20 inches one way and 30 the other, 600 square inches. On each square inch, 15 pounds of air. 600 times 15, 9,000 pounds of air. And you know, as I did before, I'll do it once again. I cannot move the weight of that air. There it is. And I say that is staggering to contemplate, the push of the air. Of what usefulness is this? Oh, well, without air, birds couldn't fly and airplanes couldn't fly. Indeed, talking about flying, here is an instrument called an altimeter or an altimeter. What does it consist of? It consists of a little chamber which is highly evacuated. I'll try and draw that little chamber which is highly evacuated. Here it is. Highly evacuated, and it has a lever system on it with a scale. Now, if we go high into the atmosphere, the air inside expands a little, the cover lifts up and pushes the lever down, so we get a reading of the altitude in terms of the pressure of the air. Or, if you wish, another use made of the atmosphere, which has so much to do with the events of weather. Here is an aneroid barometer, which has inside it exactly the same thing. The response of the chamber to increase and diminution of pressure gives rise to a reading, and I invite you to look up the word aneroid, because what does it mean? It means without, a meaning not, and neros, wet, without wetness, so it is not a mercury in glass barometer, but a dry barometer. And talking about a mercury in glass barometer, here's something you can do. Take a long glass tube about 1 meter long and fill it with mercury. It's closed at one end, closed at one end, fill it with mercury, then take a vessel in which some mercury resides, turn the tube upside down, of course with your finger across the open end, submerge the open end in this vessel of mercury, and take your finger away. Remember, the tube is filled with mercury. What would you expect? You would expect all the mercury to fall out. No, it does not. It falls to a certain level, and notice the shape of the meniscus, the shape of the surface. It falls how far? So that this length is about 76 centimeters, or about 30 inches. And that is 1 atmosphere which sustains this column of mercury. And here is a region highly, highly empty of everything, except a little mercury vapor, perhaps. So one of the best vacuums we can get is produced by such a performance of a mercury column in a glass tube. Now let's see what else we could show. What else could we? Look at this. Isn't this fantastic? Indeed. Oh, I have another one. I have another one, and since it enchants me, I'm going to do it. This was boiling over there. Here it is. Notice, I'm in a hurry. Listen. There it goes. Notice I thought I had not boiled the water long enough, because if there was any occluded air in there, we would have trouble. And so, are you not agreed that atmospheric pressure is a staggering thing to witness? And I thank you for listening. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is a very important subject, which is commonly referred to as centrifugal force. Centrifugal force. And I'm going to put the word centrifugal in quotation marks because it is so badly, falsely, erroneously, incessantly badly used. Illustration. Here I have a ball on a string, and I whirl it in a vertical circle. If now at the top of the path, let us say, or at the bottom of the path, I let it go, I cut the string, does the ball go radially outward from the circle? No, it does not. It goes tangent to the circle at the place in question. Like that. I'll show you that letting it go at the top. So, I point out by this argument that there is no force radially outward on the ball, a notion which is often badly used. Now, as an illustration of what I mean, here I have a little chamber in circular trough, tube, in which reside 2 spheres. And they lie at the bottom here. Question. I want to get one up that end, and I want to get the other up that end simultaneously. How do I do it? Obviously, spin it about a central vertical axis, and there they go. Now it is commonly said that centrifugal force drove them out. But since this is not intended to be a lesson in physics, I can only say that that argument, that notion, is quite wrong, as we will see in subsequent demonstrations. There is indeed a little toy connected with this, and I would have you see it, because it's quite enchanting for beginners to learn about the forces involved here. Here is a little circular trough, a toy indeed, in which reside 2 spheres, as in the bigger apparatus I used, and you will see that they lie one on each side of a partition. Question. I want to get one into a recess on one end of the tube and the other into a recess on the other end of the tube simultaneously. Solution. And when you play with your classmates with this, if one doesn't know it, you can always turn your back and surreptitiously, sort of secretly, spin it. I'm having a little trouble, but that is the way nature. There I have it, and each resides in its own little chamber at the ends of the trough. Now, I showed you in this demonstration that the spheres went outward. I now want to do a very classic thing which raises an interesting paradox. I have here another rotating mechanism. On this end there is a candle which I'm going to light, and I put a little chimney around it to protect the candle, and on this end there is another candle which I'm going to light, and I put a chimney around it to protect it. And now I am going to rotate this system about a central axis. And the question to be asked is, what do the candle flames do? Well, there are many possible things the candle flames could do. They could lean out, they could lag behind, they could lean in, they could lean out and back, which is sort of diagonally. They could do many things. But the reason I call this my candle paradox is that they do what is least expected. Watch, and we shall see them lean in. Watch it. They are leaning in. They are leaning in, which is an amazing thing. Regarding this fictitional centrifugal force, supposing we had some water in this bucket. You know, one of the classics of all time, you can swing the bucket in a vertical circle and the water will not come out. Question, in the case of the ball on the string, whatever I did with that, oh, it's gone. If I swung the ball too slowly in a vertical circle, is it not true that at the top of the path, here I have it, and I'm going to show you, is it not true that if I am not going fast enough, the ball won't make the circle, it'll fall down? Question, supposing I have some water in this bucket, and I do this with it, and I don't go fast enough at the top, will the water fall out of the bucket? Nearly everybody says yes, but that's not true. Answer why. When the bucket is up here and the water is starting to fall down, the bucket falls down at the same rate, so the water does not come out of the bucket. So you see, this is an old fable, very falsely treated. Consider some more of the same. I have here two vertical steel hoops, which are fixed on the bottom, but free to move on the top of the central shaft, and I'm going to put these into a rotator, which permits me to spin the thing fast about a vertical axis. And I want you to see what happens, and we could then very reasonably say this is why the Earth is flattened at the poles. Watch it. I'm going to speed up the rotational speed about the vertical axis. Now, the consequences of the Earth's rotation on its own axis, about 1,000 miles per hour at the equator, because doesn't a point on the equator go 24,000 miles, 25,000 miles around in 24 hours? There is much consequence to this. Persons weigh less at the equator than they do at the poles for two reasons, both of which I'll leave to you to explore. Consider another consequence of this high-speed rotation. Here is a thing called a governor. There is a sleeve here on a vertical shaft, and if I spin this system fast enough, you know what will happen. The spheres will move in this fashion. The sleeve will move up on the central shaft, and it could well intercept a valve here, which would shut off fuel to the motor, and that's why it is called a governor. Oh, notice I'm pretty nearly on dead center. There it is, there it is, there it is, there it is, a governor. Here is one that you can do, utilizing this fictitious force of centrifugal stuff. Here is a coat hanger, and here is a coin, a penny, the lowest coin of the kingdom, I guess, and I'm going to put that coin at rest on the bottom part of the hanger, and I'm going to swing this hanger with the coin on it in a vertical circle, and I say I can keep the coin there. Why? The coat hanger will exert a force on the coin just as the string exerted a force on the ball to keep it moving in a vertical circle. Watch it now. Somebody says, well, I hope it doesn't work, Professor, because, you know, well, if it doesn't work, then I've lost my professional dignity, but there must be a reason why it doesn't work if it doesn't. And remember, we don't ever say that the experiment failed. Watch it. Oh, it did go around 2 or 3 times and then flew off. Let us consider now another classic, which is really quite astonishing. Here is a glass tube through which a string passes. And I have named this demonstration the string in the glass tube. Notice the elegance of that. A string in a glass tube. I've named it the string in the glass tube. Now here on this end of the string is a little 10-gram weight, and here on this end of the string is a 100-gram weight. Now you know that 10 grams can't hold up 100. Of course not. 10 cannot hold up 100. But I'm going to do something to the little one and thus give birth to a strange force which will hold up the 100. Watch it. There we are. There we are. The 10 is holding up the 100. Indeed, I'm going to make it lift the 100. There it is. Oh, I'll do it again. There it is, lifting it. Now we must never say that there is a force radially outward on this thing pulling on the string. Oh, wait a minute. I said something wrong. And I'm glad I did, because it may lead some of you to catch me up on it. I said there is no force radially outward pulling on the string. Yes, yes, yes. There is a force which the string exerts on the body, and there is a force which the body exerts on the string, but there is no force radially outward on the body. So you see, ladies and gentlemen and boys and girls, in the heat of this argument, I could very well make an utterance which the good people will quickly detect. And I'm glad I detected it, so you will see that there are occasions when I say things that are not right. Consider another of this business called centrifugal force. Here is a flexible loop which happens to be of rubber. I sometimes use a chain. Very flexible. It hangs quite limp-like. Now what do? I put it on a circular disc, and I rotate that disc at very high speed on a rotator such as I had here. And then I trip off the chain or the loop. Now look what happens. There is the circular disc. Here's the chain around it. And I bring this up to a high speed. And I trip it off. Remember, the chain was a limp structure. And what does it do? It rolls away as a rigid, solid iron hoop, for reasons which I leave to you to explore. Now, since I am given to the physics of toys, I ask you to consider another interesting little thing concerned with rotational motion. Here is a little toy which can shoot a hoop. A hoop. I will not reveal any of the secrets, but there is a rubber band which can give rise to a torque to turn the hoop. And, well, notice, it was an accident, but that's all right. I'm going to shoot the hoop away. Question. You will see the hoop roll away, and then you will see the hoop roll back. Or have I said it correctly? Let me invite your attention to this enchanting little business. Watch it. There it is. Now I'm going to do it again because I like it. Uh-oh. And if I like it, that's reason enough to do it. Watch it. There it is. There it is. And I want to know what is going on. So you see, boys and girls and ladies and gentlemen, another bit of my philosophy here, my instructional philosophy. It is not always to answer the questions, but to raise some interesting dilemmas. Why things are so. Why things are so. Now, let me see what else we have here. I am not a cowboy, but the question arises, how is it that a cowboy can make a lariat or a lasso, L-A-S-S-O, often mispronounced lasso? How can a cowboy make the thing go in a circle, in a ring? Well, there it is. Notice the circular shape it took up. And the question arises, why is it circular? Interesting dilemma. A jug of water. Do you see again, ladies and gentlemen, and boys and girls, again some more of my philosophy. I use often the most plebeian and humble and simple and trivial things to demonstrate these wonderful properties of nature. How can I most quickly empty this jug? Watch it. There it is, and I thank you for giving attention to our business. This is the quickest way for the water to come out of the jug. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is the enchanting phenomena associated with things that roll, rolling things, hoops and spheres and discs and the like. Consider the following. I have here a board which I can use as an inclined plane by raising it higher or making it lower, and here is a block of wood. We all know that if I raise the plane high enough, there comes an angle, there's a little stickiness there comes an angle at which the block slides. Indeed, if I had a block twice as heavy, we would find, if we explored it experimentally, that the block twice as heavy slides at the same angle as the one block alone. And I'm going to write the mathematics of that for you so you can have something to think about. It says, the mathematics says, that mg sine of theta is equal to mu mg cosine of theta. And from the algebra, you know, I can divide out the m, so the mass of the body does not matter when things slide. Now, when we consider things that roll, another interesting and enchanting detail arises. Here I have a disc of wood wherein we see the mass uniformly distributed. There is some everywhere with respect, say, to a central geometric axis. Here we have a hoop. The hoop has another property. All the mass of the hoop with respect to a central geometric axis is in the periphery, in the edge. So now, this brass hoop and this wooden disc have the same mass, but their distribution of mass is different. If then I put them at the top of the plane, since we see also they have the same diameter, the same radius, the same surface contact, which indeed doesn't matter a bit, we ask, how do they roll when I let them go? Do they roll together, that is, keeping neck and neck? Or does the disc win, or does the hoop win? And I'm going to show you how this does indeed come out. Watch it. And so we see the disc winning. Now I'm going to roll another disc. Here is a disc, aluminum, much smaller than the hoop, and I'm going to roll these together. This is a disc and still the hoop. and the disc again wins. Now I'm going to roll these two discs together. Small disc, big disc. It will be a little difficult to check this, but if our provisions for nature were of an adequate sort, I could show you the following phenomena. Watch it. Did we not, I must go further, did we not see this disc beat this hoop? Did we not see this disc beat this hoop? Let me take another hoop. Here is a hoop. Well, it's a long one with a long axis, but it's a hoop. And here is a disc. Watch now. This disc is beating this hoop. This disc is beating this hoop. Here is another hoop and another disc. This disc is beating this hoop. Let me take another hoop and a disc. This disc is beating this hoop. And what am I getting at? I'm getting at a most astonishing discovery. First, if I rolled all the discs in the world, I would find that all discs roll alike. I would find that all hoops roll alike. Little hoops, big hoops, fat hoops, skinny hoops, they all roll alike. Big discs, skinny discs, here is a disc, here is a disc. Now, because it has a long axis, we call it a cylinder, but I'm going to show you that that disc behaves the same with this hoop as other discs did. Watch it. And so I'm going to tell you another secret. All discs roll alike, all hoops roll alike. Now all discs beat all hoops. All discs. So now somebody says, Professor, you have not lived long enough to roll all the discs and all the hoops in the world, so how do you know that? Indeed, no one has ever rolled all the discs and all the hoops in the world. But I have rolled discs and hoops in America, in Canada, in Africa, in Australia, and always I find that all the discs I rolled roll alike, and all the hoops I rolled alike, and all the discs I rolled beat all the hoops. Now, I'm going to give you the argument, the proof that all discs roll alike. Here it is. I'm going to write some mathematics. FR equals I alpha. And somebody says, what does that say, Miller? I'll tell you what it says. It tells me that if I put the right stuff in there for the force and the radius and the mass distribution of the body called the moment of inertia, I get an expression for the angular change, the angular acceleration. Or I could write the potential energy at the top of the plane is equal to the kinetic energy of translation plus the kinetic energy of rotation. What I am getting at here, boys and girls and ladies and gentlemen, is this, that a proper understanding of the affairs of nature lies in the mathematics which describes it, because words are very weak. Now, I said that all discs roll alike and all hoops roll alike. The question now is, how about some spheres? Well, here is a big sphere, here is a middle-sized sphere, and here is a baby sphere. And if the board met my requirements and I let them all go at the same time, they would keep equal separation, and I would make a further announcement. The further announcement, all spheres roll alike. Now, the hoops that I spoke of have to be very proper hoops with all the mass in the periphery. The discs must be very proper discs, all the mass uniformly distributed, and the spheres must be very proper spheres, uniform mass distribution. The only question that remains now is this. If a disk beats a hoop, and all disks beat all hoops, and all spheres roll alike, how do spheres and disks and hoops roll? Well, we know this beats this, and so the question is, where does this come in the game? Well, look here. If I roll the sphere, excuse me, if I roll the sphere with the hoop, and something wins, watch it, I assure you that the sphere wins. You now know that spheres beat hoops, but what do spheres do with disks? Ho-ho! A wonderful thing. Watch it. We have a little trouble with this board, but that's another piece of evidence that when you deal with nature, spelled with a capital N, you must make such requirements as she demands. A little difficult to show it, the hazards of experiment, but I'm going to tell you. All spheres beat all disks. So if all spheres beat all disks, then all disks beat all hoops. If we let them go at the top of the track, the spheres always win, the disks come second, and the hoops last. Now I said that all disks roll alike. Here are two disks, and without revealing their nature, I'm going to roll them. Watch now. I'm going to roll them. Oh, one is winning, and yet they look like two uniform disks. No, they are not. So I have to reveal the secret. This disk, this one here, has some weights at the center. This one has the same weights on the edge. So you see, when the mass is farther from the geometric axis, the motion is slower. And I'm going to show you that. Here's the one with the weights lodged in the periphery, and here is the one with the weights lodged near the center. Watch now the motion. There it is. And so we uncover a most remarkable thing. And I would invite you, wherever you go in the world, find a disc and a sphere and a hoop and roll them and see if what I say is not true. Now concerning rolling bodies further. You all know what a yo-yo is. Here is a yo-yo. But before I go to that, I want to remind you, the only reason this body can roll, the only reason this body can roll is that there is friction between it and the inclined plane. Without friction, there can be no rolling. Consider the behavior of your automobile wheels on a very icy surface. They cannot roll. Accordingly, in the playing with a yo-yo, what do we find? What is a yo-yo? A yo-yo is a disc with a central axis around which is wound a string. So this is a body rolling on an inclined plane, which is usually vertical. Watch it. Oh, now do you see? There is not enough friction there for the gripping to climb back. Watch it, and I hope it doesn't work properly, because that will prove the point I wish to make. Oh, notice. Oh, there it is, there it is. It is not climbing back. If the friction is adequate, a very enchanting thing arises. Here is a yo-yo, a big one, with a small central shaft, and I'm going to let it go. And the point I wish to make here is this. When it gets to the bottom of its route, there is felt a sudden jerk, yank, pull impulsively in the string, and the thing changes direction and comes back up. How far can it come up? Never to the height from which it was released. Why? Because the energy of a system always goes toward less. Watch it. Well, we had a little trouble with the twisting of the string. One more business regarding rolling things. And I invite your attention to this because it is a very powerful question. Supposing I had a wheel rolling without slipping on a surface, and I considered some point on the wheel. And I ask you, as the wheel rolls, what kind of a path does this point make? What kind? Well, some people draw something like this. And all kinds of twisty matters. I'm going to show you because it is a very important business. The point on the wheel does this. And that curve is a cycloid about which you should read because it has stirred mathematicians for hundreds of years. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our business today is the classic adventure of Archimedes about the 3rd century BC, with some wondrous things to report. First, consider a body, a lead weight, which I hang on a spring scale, and the scale reads so much. I am not interested in what it reads, but it reads the weight of the body. Now let me submerge this body in a vessel of water, and we see a remarkable thing, a very remarkable thing. As I submerge it, the scale reads less and less and less, and I urge you to see that the weight is not resting on the bottom of the vessel of water. Accordingly, when I submerged the body, the water pushed up on it, provided a buoyant force, as we say, which Archimedes discovered in his classical bathtub experiment. Eureka, eureka, I have found it. Now, how much is the push up of the water on a body submerged? Archimedes said it this way. When a body is submerged in a fluid, that's either a gas or a liquid, we're talking liquids here. When a body is submerged in a liquid, it is buoyed up by a force equal to the weight of the liquid displaced. Now, I can prove that. Here I have a vessel which has an overflow spout, and I'm going to put a little water in it to be sure the water is up to the level of the spout. There it is. It's coming out there somewhat. And now I'll wait until it stops. The water is up to the level of the spout in this chamber. Now I'm going to get rid of that water. Now what am I going to do? I'm going to submerge this body in that chamber of water, and as anyone in his right mind would recognize and attest, will not some water be pushed out? Indeed, and I'm going to push some water out and catch it in that little bucket. Watch it now. And of course, again, the scale will read less, but I'm not interested in that this time. I'm interested in the water that gets pushed out. Watch it now. And I'll wait till all that's going to be pushed out is pushed out. That's good enough. Now, what would I do with these adventures? Well, first I would have noticed how much less the scale read when the body was submerged in the liquid. Suppose it read less by 10 grams. Then I weigh this water in this bucket. And what would the water in this bucket weigh? 10 grams, meaning that the body was buoyed up by a force equal to the weight of the water this body displaced. Archimedes' principle. Fantastic. Now, I said that the water pushes up. I'm going to prove that. Indeed, you should recognize it already from your adventures by the sea, when you walk into the ocean, do you not discover that the deeper you go, the less push your feet have on the earth below, because the water is buoying you up more and more the deeper submerged your body becomes? Here I have a glass and a hole in the very bottom, and I'm going to push the glass down. The evidence that the water pushes up will be witnessed by the water coming up into that hole. Watch it. There it is. There it is. And I say the water pushes up. I'm going to prove that in another way. Here is a glass tube and a plate on a string. And I'm going to put the string through this glass tube. And now I'm holding the string in hand. And obviously, since the plate has weight, if I let go of the string, the plate will fall down. Watch it. Well, of course, says anyone who's watching. Doesn't that professor know that if you let go of the plate, it'll fall down? Of course it'll fall down. Now I'm going to prove again that the water pushes up. Well, how? I'm going to put this into the water, and instantly I make connection with the water. I'm going to let go of the string. When I let go of the string out here, the plate fell off. The plate will not fall off in there. Watch it. There it is. And you see water rushing into the inner cylinder, climbing higher and higher. And everybody says, well, when it gets the same height inside the vessel as outside the vessel, then the plate will fall off. And I'm going to leave that for you to think about. But now, my new adventure. Archimedes' bucket and cylinder. I have here a little bucket, very nicely formed, and a solid cylinder which fits it exactly. And here's what I'm going to do. I'm going to balance this bucket. I'm going to balance that bucket with the cylinder below. Let me see if I can represent that. Here is the cylinder below. And remember, that solid cylinder fits that bucket exactly. And I'm going to balance this with some weights over here. Put the beam balance in equilibrium. Then what am I going to do? I'm going to come up underneath with a vessel of water in this fashion. Vessel of water, so that I submerge the solid cylinder. The equilibrium in the balance will be destroyed, as we might say, because why? The water here is pushing the cylinder up. How much is it pushing the cylinder up? It is pushing the cylinder up with a force equal to the weight of that water displaced. And how much water is displaced? The volume of the cylinder. And how much is the volume of the cylinder? The volume of the cup. Accordingly, with the equilibrium destroyed because there is a lift, a buoyant force here, I am now going to pour some water into this little bucket. Water, 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 water. Oh, ho. When this bucket gets full, what will we see? An absolutely enchanting thing. We will see the equilibrium restored. Now I have such a bucket and cylinder. There's the cylinder, there's the bucket, and I have put it in equilibrium on the scale. Now I'm going to bring up this water and submerge the lower solid cylinder. I hope you see that the equilibrium has been destroyed. The balance is no longer in balance. Oh, I came up too high. Now I am going to fill the little bucket. I'm having a little trouble here being steady. I'm going to fill the little bucket, and the equilibrium, which does not now exist in the scale reading, will be restored. Watch me now. Oh, I filled it over much, and there's a very high meniscus. So, Archimedes' bucket and cylinder. The proof is very beautiful. A body is buoyed up by a force equal to the weight of the water displaced. Now, regarding buoyant forces and bodies that sink and bodies that float, here is a vessel of water and here's a piece of wood. Floats. Here is another piece of wood. Wood, water. Huh, heavier than water. Lignum vitae. Here is a piece of wood. Heavier than water. So there are woods that sink and woods that float, their densities being less or more than that of water. Now, regarding bodies submerged in liquids, I have here something absolutely enchanting. Here is a vessel of water in which I'm going to put a wooden ball. There. It sinks about, I don't know, 5/8 or something like that. Now here is a vessel of mercury. Vessel of mercury. I'm going to put the ball in the vessel of mercury. Watch it. It doesn't sink at all, hardly. Hardly. It rides on the very surface. But that's wood. Very light. How about steel? Oh-ho! You know that the specific gravity of steel is about 7 or 8. The specific gravity of water is 1. You know that steel sinks in water. Watch it. Sinks to the bottom. By the way, I say steel sinks in water. On an earlier program on surface tension and the strange behavior of the free surfaces of liquids, I showed in a demonstration where I float a steel needle on water. So steel can be made to float on water. But how about the steel ball in the mercury? Watch it. Oh, this is something. There it is. There it is. The steel floating on the mercury. This is a marvelous thing. Let me use a larger steel sphere, because this is enchanting to see. There it is. Steel floating in mercury. Now, talking about Archimedes leads me to show you a classic mosaic. You remember that Archimedes defended the city of Syracuse when it was attacked by the Romans under the general Marcellus. And then Archimedes was put to death by a Roman soldier who ran upon him while he was doing a demonstration in the sand. So here is that mosaic, which I hope you will see. There is the Roman soldier urging Archimedes, "Come to my general Marcellus." And Archimedes begged him, "Let me finish first my demonstration." And here is another monument to Archimedes, which shows him holding a mirror. This is a little glossy and hard to see. Holding a mirror with which, you remember, he set fire to the enemy ships far from shore. So, what have we discovered here? The remarkable principle of Archimedes that a body submerged in a liquid is buoyed up by a force equal to the weight of the liquid displaced. Now, Archimedes, as you know, apart from being a natural philosopher of the first magnitude, was also a mathematician. And I want to tell you quickly about some things he discovered of a mathematical nature, because they are enchanting. And here they are. Here I have a right circular cylinder, and here I have a right circular cone, and here I have a sphere. They are the same altitude and the same radius. And what did Archimedes discover? He discovered, by playing with these, filling them now in turn with sand, that the volumes were uniquely related in the ratio of 1 to 2 to 3. I'll leave it to you to discover how that ratio goes with respect to the bodies. Now, in his later years, having made many discoveries of great moment and significance, he was asked what he viewed as his greatest, and he referred to this: the ratio of the volumes of the cylinder to the cone to the sphere, and asked that when he dies, such a matter be put atop his tomb, which shows a cylinder, a sphere circumscribed by a cylinder. So here is a sphere about which is circumscribed a cylinder, and this was put on top of Archimedes' tomb, buried near Syracuse. Where are we then in this dialogue? Archimedes, 3rd century BC, who must certainly rank with Newton of the 17th century and Einstein of the 20th. So next time you go to the sea, To bathe, remember Archimedes. And when indeed you take a bath in your bathtub and you submerge yourself in the water and the water rises, remember the affairs here, which revealed that beautiful fact which we use abundantly, because after all, this is why ships can sail on the sea and submarines under the sea and airplanes above the sea. And I thank you for your attention. How do you do, ladies and gentlemen, and boys and girls? I'm Julius Sumner Miller, and physics is my business. And our very special business today is the work of the young Frenchman Blaise Pascal, a genius of the 17th century, who died at an early age, indeed at 39, but left enough for us to contemplate for a lifetime. And I urge you to read his life, written by his sister, La vie de Blaise Pascal, the life of Blaise Pascal. Indeed, at the age of 12, he happened one day to strike a dinner plate belonging to his mother, and it rang out, and he was thus led to write a definitive paper on vibrating bodies. I urge you to go read about him. Now, one of the principal things he had concern with was the property of liquids and of fluids, and raised a very interesting problem. Consider, let us get a picture of him. Here he is, just some few years before his death. Blaise Pascal, a genius of the 17th century. Consider the following. Supposing I have a vessel shaped like that, another one with the same base shaped like that, and another one with the same base shaped like that. Three identical vessels, that is, the bases identical, and now I fill them with water to the very same level. Water, water, water. Question: on the bottom of which vessel do we have the greatest force? Answer. Discussion. Most water here, most mass of water, most weight of water. The bottom here supports all the water bounded by those vertical lines. The bottom here supports the water bounded by those vertical lines. The bottom here supports the water bounded by those vertical lines. Well, says somebody, I see water in here and water in here. What holds that water up? Answer: the sides. Then somebody says, there's no water in here and no water in here, and yet the push on the bottom is the same. Answer: yes. Reason: the walls push in with a force which compensates for the water which is not there. And I'm going to show you this with a wonderful experiment. Here it is. Here it is. Here is a narrow-walled vessel, and I'm going to fill it to a certain level by raising a chamber of water. Here comes the water, here comes the water, there comes the water. Hold it, right there. I'll get the water level in here proper as measured by the position of this marker. And if we read the scale, it reads about 43 or 4. Now I'm going to let the water run out of there and replace this vessel by a very big one, quite like the middle vessel that I drew on the board. And I hope you see that this vessel is vastly bigger than this one, but they have the same bases. They have the same base. I'm going to screw that on there, if I can do it here. There we go. And now I'm going to raise the water in here to the same level as in the other one, and I hope you will see that the gauges read the same. There's always a little trouble with the linkage system in such a mechanism, so there may be a little trouble, but I'm bringing the water up to the same level. Since the sides are flared out, the rate of growth of depth is less, but there we have it. Oh, I've exceeded the level a little bit. I'll come down a little. I'll come down a little. And I think that's evidence enough that the readings are identical. The readings are identical. Amazing piece of business. Consider another consequence of Pascal's work. Supposing I have a little chamber here connected to a big chamber here, and I put a piston in this chamber and a piston in this chamber, and this is filled, of course, with some incompressible fluid, oil or water. You are aware that if I push down on this piston, the water goes up there and lifts that piston. This is an hydraulic press. If indeed I make this a compound machine by attaching a lever in this manner, and I apply a force here, I can pump the liquid from here down and lift an enormous load. Indeed, if this piston is very small compared with that one, I can multiply the force I apply here, depending upon the length of this lever, thousands of fold. And I'm going to show you that. Here I have such a system. Here I have such a system. A little piston right here, and a big piston right there, and here is a block of wood. Here is a block of wood. And I say it takes about a ton of force to break that wood, and I can't do it with the unaided hand, but let me put it in there. I made a little mistake. I have to come down a bit. Watch it now. Watch. I am going to deliver. And here is what I wish you all to see. That with ever so tiny a force applied out here, with my little finger, I can produce a force of about 1 ton at the middle of the board above this piston. Watch it now. Watch the scale. Oh, well, this board broke at about 1/2 ton. Now, you know very well that I could not exert a force of 1/2 ton with my naked hands. Here is a board, a piece of 2 by 2. I would say that it will take about 2 tons to break this. About 2 tons. Now watch it. This is fantastic. Applying Pascal's view that the liquid is incompressible and any small force applied here is felt without loss in all parts of the machine. Watch it now. There it reads 1.5 tons. There, it fractured at something around 1.5 tons. And I say that is fantastic. Oh, staggering, staggering. The forces which we can impress here. Now, I could show you another experiment with that hydraulic press. Here is a spring. I will not pursue the adventure, but this spring has an enormous modulus, meaning that it takes extraordinary forces to squeeze it together. More than 2 tons, in fact. I couldn't do it with the naked hand, but there I could do it very easily. Let us consider another consequence of Pascal. Here's one of very great usefulness to the human race. Here is a hypodermic needle. Question: why is the needle sharp, very pointed? Answer: for the same reason that you wear snowshoes to cross deep snow. You spread your force out over a large area, so the pressure, which is the force per unit area, is very high here in the needle. For example, ladies with high heels. A little girl weighing 100 pounds can leave more impression on an earth road than an elephant. Imagine that. Why? Because her weight is on so small an area. So here we have it. I push with a force of 10 pounds with my thumb. The hypodermic needle has a pointed area of about 1/1000th of a square inch. The pressure is 10,000 pounds per square inch. Fantastic. Fantastic. Consider another one. This is beautiful. Here I have a flask filled with colored water, 1-hole stopper in a glass tube. And I call your attention to the level of the water right here. I hope you can see it. The level of the water right there. A little difficult. There, that's very good. Beautiful. Now, what am I going to do? I'm going to squeeze on the wide sides of the glass. And we see an astonishing thing. Watch the level of the water. Watch it. There it goes up. Suggesting two things, that the glass is very elastic and the water highly incompressible. Another adventure with the same thing. Let me turn the glass sidewise. Let me squeeze on the narrow sides. Question, what will the level of the liquid do? Answer, when I squeezed the wide sides, I deformed them inward, diminished the volume of the vessel, and up went the liquid. When I squeeze them on the wide sides, will I not bulge out the wide walls, and will not the liquid fall? Watch it. There it is. It goes down. Another adventure which you can pursue, the Cartesian diver. Here I have a little creature in the shape of a man in which we have put some water, and he floats at a certain position. There is some air above the column of water. There is some air in him. What am I going to do? I'm going to push down on that rubber sheet here. That force by Pascal is communicated without loss to all parts. The water in here feels it. The water in him feels it. The air inside of him feels it. And because the air is compressible, it gets compressed, more water goes in, and he goes down. So you see, it is not me pushing that pushes him down. It is this sequence of actions. Watch it. There it is. I love that little business. And, whoop, I can stop him where I want. Since they are differently loaded, they ride at different positions. Now you can make one very easily. You don't need such a thing as that. A little medicine vial would do, such as little pills and the like come in, and here it is. Here it is. There it is. Like a submarine, in fact, exactly how a submarine works. I release the force or the pressure, and up he comes. Consider another consequence. Let's go over here, back to this table, because there are some enchanting things. Here is an experiment which we could do, but we will not. We will consider it a virtual demonstration. Here is a flask, filled completely with water, completely, with a tight-fitting stopper. Liquids, I say, are incompressible. Conclusion, I can deliver a sharp, impulsive blow to that stopper. So, that force would be felt in all parts of this chamber, and it would burst into 1,000,000 bits, and the water and glass scatter. Enormous. Why? Because Pascal said any force delivered to a liquid is communicated without diminution, without any lessening, to all parts. Another one of the same kind. Here is a wooden block with some nails in it, and here is a flask. Unfortunately, this flask has a bubble in it, which I think you can see. And bubbles of air are highly compressible. I cannot, therefore, do what I want to do. But supposing I fill the flask completely full of water, I could then use it with absolute immunity to drive that nail into that block. Why? Because water is highly incompressible, and the vessel would feel nothing. This would act like a solid hammer. Another consequence of Pascal and of Torricelli. Beautiful thing. I have a can here filled with water, and I hope you can see on a close shot that there is a hole in that can, and yet the water does not come out. And I say, that's fantastic. I'm going to pull out the stopper. Watch it. I'll give you evidence that there's water there. There it is. I put the stopper back in. The water has ceased running out. Question, what's holding it in? Obviously atmospheric pressure. Question, very important. How tall a can could I use to do this? Answer, 34 feet. Isn't that fantastic? Fantastic. Now, one more demonstration. One more. I have here a U-tube. A U-tube. That's a tube shaped in the form of a U. Mercury in the bottom part. Water-colored above it, and you see there is a difference in levels in the mercury columns. What will be the ratio of the water level to the difference in the mercury levels? Answer, 13.6, which is the specific gravity of mercury. And I invite you to do this experiment and wish you good fortune. How do you do, ladies and gentlemen, and boys and girls? I am Julius Sumner Miller, and physics is my business. And our very special business today is the subject of simple machines. Simple machines. Now, when you study these matters in school, it is usually said that these are the 6 simple machines. The lever, or as some pronounce it, the lever, the inclined plane, the wheel and axle, the screw, the wedge, and the pulley. And I wish in this program to show that really all of these reduce to only 2, the lever and the inclined plane. And what is better for us to contemplate is the following, that all of the things I will have to deal with here today are the most plebeian and simple and homely and commonplace. And my purpose is essentially this, that when you pick up your fork and knife to eat your dinner, I hope you would recognize that you are using some levers. Indeed, the sharpened blade of the knife is an inclined plane in addition to the tool itself being a lever or lever. And how about the prongs of the fork? The prongs of the fork are usually sharpened a little bit, so they are wedges, and wedges are inclined planes. So let us go at random to some of the things we have here, and you will see exactly what I mean. Consider, for example, the following. Here is a block of wood in which I have already lodged some bolts and screws and other things. Here is a screw, and I'm going to attempt to lodge it further into the wood with a tiny screwdriver. A tiny screwdriver. No success. Why? Well, let us look at what really happens. The handle of the screwdriver I have enlarged, looks like that, and I apply a force this way and a force that way, so that I turn it about a central axis, and these 2 forces, equal and oppositely directed and parallel, are said to be a couple, C-O-U-P-L-E. You see a couple of forces acting in this way. Now, the small screwdriver had too small a radius. So what do? I use a big screwdriver, and the same force will accomplish my purpose very readily, as you will see. Here is a big one. And the handle, of course, is very much bigger, so that the torque, or the turning effect of my force, is very much increased. There it is. Beautifully accomplished. Consider now, I remark that a threaded cylinder, which we call a screw, is really an inclined plane. And I hope you see the inclined planeness in this threaded shaft. I'm going to prove to you that it's an inclined plane. Here I have an inclined plane cut out of paper, and it goes uphill to my left. I'm going to wrap this around a cylinder, and I hope you see that what I will get out of it is this. Here is the cylinder, and I wrap the inclined plane around, and I get a threaded shaft, which is a screw. Now watch this. Here, I'm going to wrap it around. Let me finish it here first, and there you will see the inclined threads. Now, I have wrapped this one around so that the threads go like that, which is a left-handed screw. I have cut the other one so that when I wrap it around, it gives me, I hope, yes, let me turn it over. No, there. Notice I'm a little twisted up here. Well, Notice, I'm glad I'm twisted up because this suggests that even professors of physics can get a little bewildered. I know where I made the mistake. One of these I have to turn over and use the mirror image, and then it will give me a right-handed screw. Now, this business of left-handed thread and right-handed thread, very important. Illustration. Oxygen tanks used to take care of sick people are right-handed threaded. Nitrogen tanks, on the other hand, I believe, are left-handed threaded, for the very reason that then nitrogen could not be inadvertently and accidentally fed to a patient who should be getting oxygen. See, very important idea. Let's look at another one. Here is a bottle with a screw cap, and the housewife finds that she cannot undo it because it is too firmly fixed. What does she do? Answer. Provide herself with a lever and a notched jaw, which is essentially an inclined plane. And then she puts it on there, and ever so gently, there it is. So I say that for little bottles with small screw caps, you have a small Stilson wrench, and for medium bottles, a bigger Stilson wrench, and for very big bottles, a very big Stilson wrench. And any well-equipped household, I think, should have at least 3 Stilson wrenches. Consider, for the housewives and the boys and girls and the teachers, here is a grater. Now, what is a grater? A grater, well, a grater, you grate with a grater. There it is. And I say a grater is an inclined plane. Very clearly an inclined plane. How about a wedge? A wedge. A wedge is clearly an inclined plane. Consider the following. Here is a railroad spike. Indeed, it is pointed, quite like nails are pointed. Why? They are inclined planes, and the advance into the railroad tie is more easily accomplished because this is an inclined plane. Let's go to an ordinary hammer. Here is a nail that I've lodged in here. A lot to say about this. Let me use the hammer as a lever. Not much success. I improve its mechanical advantage by providing a block under the head, and there. And now what must I say? What must I say? Very important. What do I feel when I feel this nail? Very hot. Friction develops heat, and friction is a dissipative force, always arising when work is done, and about which we spend fortunes to eliminate. Very important. But remember, if we could accomplish the elimination of friction, no motion whatsoever would be possible. A very terrible thing to contemplate. Here I have another one in front of me. How about a nutcracker, a lever? What happens? I put the nut in here, and then easily accomplished, effortlessly. Here's one for the housewives and the boys and girls and the mothers and fathers and the school teachers. A broom. A broom, I regret to say, is a lever. And next time you sweep the house, I wish you would have some regard for Archimedes of the 3rd century B.C. And I'm going to show you how the lever can be used in an enchanting way. The usual way is what? We hold it there and push here, push here, push here. The fulcrum here and the force there and the load down there. It can be used in another way. Watch me. I'm going to have the fulcrum here, and I'm going to push it here. Not too handsome a way to use a broom, but it can be used as another class lever. More on the same. If indeed the subject is getting, let us say, monotonous, it should not be. All these things are levers. Here is a piece of metal. Here a little pair of metal clippers. I have difficulty. Why? Not enough lever arm. Not enough lever arm. A larger shears, effortlessly. There it is, like cutting butter. Or consider a file. What is a file? A file is a succession of inclined planes. And regarding a file, I hope sometime you will be able to go to Milan, Italy. And in the Museum de Leonardo da Vinci, There are many of Leonardo's devices, and one of them is his file maker. And when I was there last, I used it and made, indeed, some scratches on a file. How about a meat grinder? Oh, nobody uses a meat grinder much these days because it's done for you. But if you will look inside, you will see that that is an inclined plane. Beautiful there. The camera catches it nicely. Here it is. Here's one of the cutting tools from inside, and you see it is an inclined plane. How about an egg beater? An egg beater. An egg beater is not a simple machine. An egg beater is a compound machine made up of a lever, the handle, and some geared wheels. And what do? We turn the geared wheel. There is a certain number of notches on the big wheel and a certain number there. The handle is so long, and so we speak of the mechanical advantage of a simple machine. Meaning what? How many times is the force multiplied when we apply a force? If, for example, with a force of 1 pound I can lift a ton, then the mechanical advantage is 2,000. Let me go further. Here is an interesting thing. Pulleys. Pulleys. Now it is very important that I say something about pulleys. When students and boys and girls study pulleys, it is usually said that to find the mechanical advantage of a pulley system, you count the number of ropes supporting the load. Now, I should say that this is not a good thing to do. It sometimes leads to the right answer, but often the right answer is gotten by physically wrong means. And this is a very important philosophy to remember. Getting the right answer is the least important of your endeavors. What must be right is the logical, analytical reasoning that leads to it. So I would urge you to study pulleys and learn how to find the mechanical advantage without counting the number of ropes. Here is a pulley system made up of 2 blocks with 3 sheaves each, or 3 pulleys each, rather, and I can lift an enormous force by the application of a small one. Notice, friction is not playing an adequate role, and so the system unwinds. And when I talk about pulleys, what name in history must come to my mind? Answer, Archimedes, because you remember he designed all kinds of machines of war in order to protect the city of Syracuse against the invasion by the Romans. And I would urge you to read the story of this great adventure as recorded by Plutarch, The Siege of Syracuse by Marcellus, the Roman general. Where am I now? Where am I? Oh, let us take some ordinary cutting pliers. What is a cutting plier? Well, we say it in the plural, pliers, wire cutters. First, it's a lever. Secondly, it's an inclined plane because the cutting jaws are inclined for sharpness. And ever so effortlessly, I cut a wire. And so, ladies and gentlemen, and boys and girls, we come to the end of this program, indeed to the end of this 15th program, and what has been my singular ambition throughout the series. It has been just this: not to teach you any physics, not to assign any lessons or any problems, but rather to point up the beauty and the drama in all of this and to excite your enthusiasm and your curiosity, for these are the foundations which will lead to your better understanding. Now, what have we done? What do physicists do? What is physics? What is science? That's an all-embracive term. Science, of course, is what scientists do. Physics is what physicists do. And what do physicists do? Physicists explore how nature behaves. And I urge you to spell that nature with a capital N. So as you go about your daily affairs, your school days, your days at home, your playing hours, I would urge you to have a regard for the things all around you, for they are filled with beauty and drama. And seeing how nature behaves will give you a full life. And I thank you for listening.